wired to that. Yes. Okay, hey everybody, welcome to today's stream. Happy to see you all here. I hope you're all hyped up for some PCB action. And yeah, so maybe to kind of take that expectation out for now, we won't be doing any breadboarding. So this is solely focused on PCB design. And the general idea is basically what I want to do is I'm kind of assuming that you are maybe somebody who has already built some things on a breadboard, maybe even soldered some stuff on the strip board, and now you would like to get into PCB design. Now, this might be a bit kind of daunting at first. I know it was for me, because I like I just kind of explained, like I did that. I started out with just breadboard and then strip board, and strip board seemed like very approachable because basically you don't have to order it from anywhere. You can buy a strip board like at the store on the corner, and then you can make your own layouts. You can make it all at home. It's done, and it seems like at first it seems just very risk-free. But if you're like me, then at some point you kind of realize that stripboard has a bunch of drawbacks, which, I mean, first of all, is just the fact that you have to kind of make the layout anyway. You have to kind of do the concept. You have to use software, or like I do, like draw it on paper. And then in the end, you have to kind of still like prepare the strip board, you know, like you have to cut the copper strips to kind of make the layouts work. And it's just overall like a very tedious process, I feel. It's not very like repeatable. Of course, if you have a layout, you can rebuild that. But you have to like go through all these steps, you know, of cutting the strips, and then fitting all the components. You have to kind of remember where everything goes. It's not very intuitive. And then the worst thing for me was always solder bridges, which kind of happens when you apply a bit too much solder, and then it kind of spills over onto the next strip, and then you have a connection between two strips that should not be connected. And the problem for me always was that sometimes these solder bridges, these connections are maybe like quite small and not like immediately obvious. And then your circuit would just basically like misbehave, and it's very hard to figure out like what's going wrong. So this kind of at some point drove me to doing PCB, because with PCB, there are a bunch of advantages. For example, once you have created a layout, you can just order as many copies of the PCB as you want. You don't have to prepare anything. You just order the stuff, you get it in the mail, and you just have to plop in your components, solder them down, it's done. Also, if you space your stuff correctly, then solder bridges are quite, I wouldn't say unlikely, but it's less likely that they will happen if you kind of know what you're doing. And so, what did I want to say? Yeah, those were basically my reasons for going with PCB in the end. And now I'm just assuming that maybe you are someone who wants to go down the same route, and maybe you're kind of confused because there's all this additional stuff that you have to deal with. For one, you have to select a software tool that you're going to use to create your PCB layouts. And then, of course, you have to also order them. And there's like a bunch of stuff that might seem a bit hard to figure out at first. So what I want to do today is basically walk you through the process of designing like a very simple VCO module. So what we will do is we will take my shapes VCO that I've done a video series on. We will kind of cut it down. We will say, okay, which features can we take out? And what I've kind of determined what I want to do is I want to make it basically a sawtooth only oscillator that has one CV input, has like one tuning pot, and then that's basically it. So I really want to reduce the scope, because that allows us to kind of focus on what's kind of important here, which is like the PCB design itself. And then also I will go for a eurorack format, simply because I kind of feel kind of attracted to that format at the moment, and I know that a lot of people already have racks in that format, and that's why I think it's just a good like public format. Of course, you can most likely apply all the stuff that I tell you here today to many other formats. You can basically adapt it, but just so you know, we will be going for eurorack. Okay, with that out of the way, we should probably first talk about the choice of software, because here in the chat we already had some discussion. I think it got a bit heated. Maybe we can cool it down a bit. So the basic question is, like, if you're looking at the market, like what's out there, as far as I can see, it's probably not like a good overview, but as far as I can see, I've kind of identified like 3-ish categories. And the first one I would say I see, actually I'm not quite sure if you pronounce it this way. I always call it KiCad. It's an open source tool that you can obviously then download for free. It's quite powerful. It's kind of community driven. You can kind of extend it with plugins, and it's as far as I can tell, many people like it a lot, also because of a feature we might be talking about later, which is like free routing. It apparently takes a lot of work off your shoulders, but yeah, this is one option. Then the next option would be, from my perspective, something that's more kind of professional. I think that Eagle, like the tool Eagle, kind of falls in that category for me. I think I think there is a free version, but generally, like it's a kind of like paid software. And I think this, like I've heard, this is kind of the industry standard. Correct me if I'm wrong, but I haven't tried this, so I can't really say anything about it. And then the third category for me would be the tool that we will be using today, which is called EasyEDA. Now, there is, like many people dislike EasyEDA for good reasons. For one, it is, I think it is actually being developed by a Chinese PCB manufacturer called JLC PCB. And if they don't manufacture it, then at least like they are like very tightly coupled. So in the software, like you will see like a lot of connection to JLC PCB, and the tool has some integration there, so you can order directly from the tool from them, and this might be already enough to discourage you from using it. There are other things like the interface. Can be a bit unintuitive, it can be a bit buggy at times. So the question is, why am I using it? Why am I showing it to you? And the answer to that is basically simply because it runs in the browser. You don't have to download anything. And even though I said that the interfaces can be unintuitive and can be buggy, I still feel like it is very easy to use. So once you know like where what is, it's just a great way to kind of get started with it. And I feel like if you're a complete beginner, if you have no idea what you're doing, I think it's still a good place to start. I would encourage you to later on kind of migrate to a different tool. But I think that most of the components that we will talk about today will be applicable to other tools. The workflows might be a bit different. The menus might be structured differently. But in essence, like, I think we're doing similar work here. And of course, like one additional reason I should give is because, KiCad, like I have tried it, but because I am very, very kind of booked and I don't have much time, and I already have some experience with the EasyEDA, like I never kind of made it a priority to learn using KiCad. I know that down the line I want to do this, but for now I wouldn't feel comfortable showing you that tool, just because I don't want to bore you while you're like watching me not find stuff and kind of weasel around. So that's also why I'm going for EasyEDA. If you have a problem with this, then please put it in the chat. Like I hope I covered like all the reasons why EasyEDA might not be the best choice. If you have more reasons, please put them in the chat. I think it's good to have like a healthy discussion about which tool is kind of the best, like for our purpose. This is also something that I think it's important to keep in mind, because we as DIY synth people, we probably don't need like the most extensive, powerful tool. We are kind of in a privileged position where, I think my stream died. Oh, and I think now it's back. Okay, I'm very sorry. What was it saying? Oh yes, we're in a privileged position where, we don't have to worry that much about noise in our circuits. We don't have to think about like very high frequency applications. So yes, having said all that, how should we start? Well, I think it's best if we just jump into the software right away, and then whenever something comes up, I will kind of try to keep an eye on the chat. I will try to answer your questions, yeah. So let's jump over to the software. Don't worry, this is in German, but the editor is in. I've set it to English. Okay, so let's assume, again, you have no idea what you're doing. You want to get started. What you can do is you can go to this website, which is easyeda.com. Then you will have to create an account. And under that account, you kind of save your files. So they're basically being kept in the cloud since this runs in the browser. That's just how that works. You can download your files. You can also convert them into files that will be readable by other software. But yeah, the main means of storing things is in your account here. Okay, so let's assume you have created your account, you've signed in. Like you can see, I'm now signed in. You can go into the designer here. I hope now it's switching to English. Yeah, it's looking good. Okay. And yeah, this will be what you're greeted with. It's not the most beautiful interface, but I think it's bearable. Okay, so the first thing that we want to do is we are already here in the project tab. And what we want to do is we want to create a new project. So you can just right click here in this space and you can say new project, and then you simply give it a name. So in my case, I'm going to call this basic shapes. And that's basically all we need to do here. And now you can see that it has created this folder here, and it has opened this sheet here. And now you might ask, okay, what's the sheet for? Simple, the sheet is for drawing a schematic. And now you might ask, and this is a question that I asked in the beginning, like, why would I draw a schematic? Like, I have already maybe created my own circuit, or I have used some other people's schematics, and I have already verified them, and it's all good. Why do I need to kind of redraw them in here? And the answer is, and I think this is true for all these kinds of tools, you really, really should and want to do this because the software can help you much more efficiently if you kind of draw your schematic in here. And that's because if you draw the schematic, then the software basically knows which parts are in the circuit, and also which parts connect to each other and how they connect and everything. So then later, when we're in the stage where we are designing the actual PCB, then the software will be able to tell us, if we if we messed up, if we left out some connections, if we made a mistake. That's how that kind of helps us. And this is why we need to create the schematic in here. Okay, then the question probably is, okay, how do we do this? Maybe you haven't used any kind of like schematic editor like this before. And it is it is simple and it's also not simple. I will explain why in a second, but first let's kind of be clean and tidy about this. Let's name our sheets. So this sheet I will just name basic shapes. I will do everything on one sheet. Like, you also have the ability to create multiple sheets for the same project. To keep it simple, we will just do everything on one sheet because the circuit will not be very complex. And I think that's why this is feasible. Let's put our company here. And now we are all good to go. Okay, and the first thing that you might kind of be confused about, and this is something that I was very confused about when I started working with this, is okay. So if you look on the screen here, you can see there are some, they call them wiring tools, but this seems very incomplete. You know, there's an option here to draw a wire. There is an option to draw a bus. You have something like a ground flag. You have another ground flag. You have like a positive rail connection. But you know, there are no components here. There are also no components anywhere on the screen. And maybe I'm just a bit dense, but to me this was strange at the beginning. And then I kind of figured out, okay, so just from a usability perspective, you have to use this sidebar actually while you're designing your schematic. And what you can do here is you can access something called the EELib, for whatever EE stands. And in here you will find a bit more stuff, but it's still not very exhaustive. Like the list is still quite short, but there are some things in here that are very useful. For example, resistors. Curiously, you have separate options for the US style and the EU style. So whichever you prefer, you can use. I think otherwise they are functionally identical. You have stuff like potentiometers here. You have capacitors. These are non-polarized. You can see that because both sides are straight and there's no plus sign anywhere. Then below that you have polarized capacitors. Then you have stuff like inductors, which you don't need. You have batteries. And then a bunch of stuff that I don't really use except for diodes, transistors, and that's it. And now the problem is, okay, so still we don't have in here what we are looking for. And maybe to illustrate that, give me a second, I will get the schematic that I drew for the VCO. Should have prepared this before, sorry. Okay, let me switch over. Whoops. Okay. And now you should hopefully see this schematic. Okay. So, yeah, here is the schematic as I drew it, like for this is the latest version of the oscillator. And as you can see, there is a bunch of stuff we're not going to need. So for example, this path, like this whole thing here, is for the square wave, or rather for the pulse wave output. So we can kind of forget about all of this. So this is basically gone. And then on this side, I think I want to omit the FM input. I think I also want to omit the fine-tuning knob. So I would say we will just do the coarse tuning knob and the CV input. So these are also gone. And then if we kind of think about this in a in a structured way, like for me, where it starts is right here, because this is the oscillator's core, right? So we have the Schmidt trigger inverter, we have the capacitor, and we have the diode, and these three elements together with this transistor, they form basically the core of the oscillator. So you know, when I now recreate the schematic in the software, I want to start with this part. Now, before we jump back into the software, I think I'm going to check the chat to see if there are any questions that you already have. Okay, Marcus, I haven't convinced you to use EasyEDA. Yeah, also wasn't really my intention. So if you're already using KiCad and you are happy with it, then definitely stay there, I would say. Let's see what else is there. Okay, someone asked for the noise source. If you go to my channel and you look at the video I did for my filter giveaway, then you will see, there I'm sampling noise, from a transistor. And there I show the schematic for that. So yeah, check that out. You will find it there. Then George says, I looked up Eagle and apparently it's $350 a year now, when it used to be $500 for a perpetual license. Yeah, that's quite a steep raise. But I think I have in the back of my head that someone said that under some circumstances it's actually free. Not quite sure about that. But yeah, I mean, maybe if you only want to use the stuff kind of private, what's the word? Like as a hobby, basically, then maybe it's not the best choice. Not sure. Okay, Kunstbanause says, we cannot see your mouse cursor. Yeah, that's a problem. I'm using OBS Studio to stream. And whenever you select a window as kind of the streaming source, it will hide your cursor, which is stupid. You can't enable it for some reason. So I will try to kind of highlight stuff by dragging a box. I hope it's still understandable. Can you say something in German? What do you want me to say? Please give me something to work with. Then Circular Tonic says, do you pencil before Sharpie? Your diagrams are so clean. Thank you, first. And second, no, like what I do is I use these fine liners. Like this is a new brand that I'm trying. This is a bit annoying. Like they are, like in general, like drawing with them is nicer, but the ink smears, which is super annoying. And before I tried these, I was using the classic fine liner. These are better in the sense that they the ink doesn't smear, but the tips wear out much quicker, which is annoying. And also because, and this I think answers your question, what I do is I do basically a first pass. So I draw this whole thing once, and then it looks terrible for some reason. Like it just always looks like a child's kind of what's the word? Like a child's drawing. And then what I do is basically I with some force I kind of like redraw the lines and draw them like multiple times. And I mean, even though the drawing itself doesn't change, this makes it look like so much nicer. So yeah, that's how it works. That's also why it takes forever. So drawing this, I don't know, takes like 45 minutes, something like that. But the problem is that I really like the aesthetic, and I think it's quite unique, so I keep doing it. Also, I enjoy drawing, but it's still like a huge bottleneck. So if I have to draw like 10 sheets for a video, it can take a full day to draw. So yeah, that's the drawback there. Further questions. All the symbols are on grid. Yeah, right. So you have all the dots here, and that's why kind of it allows me to have stuff more consistent than it would normally be. Which I think greatly helps with the aesthetics. So I try to use that like wherever possible. So for example here, like with these lines, I just follow the grid, and this gives everything like this kind of geometric look, which I like. Okay. So Peter says, found some description how to show the cursor while streaming using OBS. Maybe you could find a way enabling it that way. I will look it up again. Maybe you can share it on Discord, because I don't want to do it right now and bore you. Okay, and then you were talking about the hobbyist version, which seems to be free. Yeah, definitely check that out. I haven't, maybe I will too. And then Greenbrier Studio says, I don't like cloud software annual fees. I use apps for years. I agree. I want to like buy it once and then use it. That's how I roll too. Okay, so now that we're done with that, let's get back to the software. And just to reiterate, just what I'm trying to do now is I'm trying to redraw the schematic in the software. And for that, I identified kind of the core element of the oscillator, which for me is this group of 4 components: Schmidt trigger inverter, a diode, a capacitor, and a transistor. So let's first rebuild this in the software. So I will switch over, and here we are. And now we are facing the first problem, because if we want to start with a Schmidt trigger inverter, then when we're looking here in the sidebar, we will see that there is no Schmidt trigger inverter in here. Okay, so the next question is, what do you do about that? And it is actually quite easy. So you can see here under the EELib tab, so the one that's blue, the one that's open, you can see there is the library tab, which should be highlighted now, I hope, even though you can't see my cursor. So there's this library tab, and when you click on that, then you get this very ugly modal, like this kind of windowed screen here. And what you can do in here is you can search for specific parts. Now the thing here is that you, like, since we want to design a PCB, we always need to keep in mind that we are like not only looking for like a generic part, like we are looking for already the specific part that we want to use. And in our case, like for the Schmidt trigger inverter, I think really the only choice is the 4106. People tell me that they can't decipher that number. So 40106 chip. And the reason why that's the only choice is because I think, like, to my knowledge, that's the only Schmidt trigger inverter on a chip that can handle more than 5 volts. Like all the other ones I've seen, they kind of top out at 5 or 6 volts, and everything above that will probably fry them. So that's why you can't use them for this oscillator. So since we know this, we can simply look that up. So I will type 4106 and I will push enter. And now you can see here in this, oh, I can't highlight it, sorry. Oh no, I can highlight it like this. So in this row that's titled classes, you can see a bunch of very unintuitive names like workspace, LC, SC, then JL PCB assembled, blah, blah, blah. And what that is kind of like, it's different reservoirs of parts. So I think that LCSC is kind of a partner of JLC PCB, who again, they are making this software. And so they are kind of offering like their own models and blueprints for your schematics. But I tend to avoid those. And what I usually go for is either the system components or the user contributed components. And as we can see in the system, there is one part. And we can see that it's a bit of a weird one, because for the schematic symbol, it's actually like the whole chip. Now, of course, we could use that. And I'm actually right now debating if we should use that, because the problem is, probably all know, like for my oscillator design, we need to kind of disable all the Schmidt triggers that we don't use. And so we are going to need to kind of put that into our schematic anyway. So maybe this wouldn't be such a bad idea, but I kind of do dislike the aesthetic of this. So let's just quickly check the user contributed one. Okay, so here we have. Oh, it's also not so nice. They look quite ugly. And again, I mean, you don't have to care for aesthetics here. I just don't really want to use anything that's very ugly. But now I'm kind of confused, because, I mean, you can already see, like here on the right side, there's always a symbol, and you can see like it's basically like the full chip, like as the heading, and then below that you have like all 6 inverters that are in one chip. So these are all inverters that belong to one chip. And I'm kind of confused because all of them are missing the power connections. So this is already off to a good start. So let's try to find one that has the power connections. I'm actually unsure like how it would work with these footprints. Maybe the power connection is just implied. It could also be a possibility, but they all seem to be done in the same manner, which might be another reason. It might be smart to just use the system one that has the full chip, because that one had the power connectors and everything. Okay, so here we can see one that has the individual inverters, all 6 of them, and then it has one thing here for the power connectors. But still, like, I am unsure if I really want to use this thing. I think I am going to go for this one, simply because, you know, then you don't have like so many single elements floating around the screen. I think it's maybe a bit more intuitive. If anyone already knows why that's a bad idea, then please put it in the chat. But for now, we are going to start with this part. Okay, so what I did there is I just double clicked on the part, and then what happens is that it kind of attaches to your cursor. And now you can see my cursor, which is probably great. Now all we need to do is we need to put it down somewhere. Okay, now you will notice that I have another chip attached to my cursor, which is unfortunate. So the question is, how do we get rid of this? And it's very easy. You can just click on the hand symbol here in the sidebar, and then it disappears. And now we are free to navigate again. Oh, by the way, another kind of tip is like at first I didn't know how to kind of drag the screen around. And how you do that is you simply right click, or if you're on a laptop, you can just click with both. I think with both fingers, which is basically synonymous with right clicking, and then you can drag the screen around. You can move, and also if you want to zoom, you can simply use the scroll wheel, or you can just zoom with 2 fingers. It's a bit choppy and strange, but it does work. Okay, so now what we have is we have our chip here that we want to use, right? And I'm going to check the comments real quick. Maybe there is something that I didn't see. Okay, so 5 seconds says, not a question, but I just think it's great in general how you emphasize working cleanly, whether through your schematics or in your pre-cut straight jumpers. Yeah, I just think it just saves you so much trouble down the line. It's always better to put in a bit more effort to work clean, other than kind of at some point looking back on a big messy pile of stuff that you did, and then you're completely not motivated to go back and fix anything, and it just stays messy. So I think going like that, doing stuff clean is always the better option. Then, okay, you are talking about subscription model. Fair enough. There might be some upsides to that. Raketensesso says buttons get highlighted. That's good to hear. Okay, Ken says the CD14106 is an exact equivalent for the 4106. Okay, so you could probably also use that one, yeah. But I mean, most questions that I get are for the 74. I don't know what the exact number is. Like there's kind of also a hex Schmidt trigger chip that starts with 74, and those don't substitute. Those will not work. Okay, Droning Brightness says, thanks for following through with PCB design. Sure. Like so many people asked for it like after my filter video, so I thought might be a good idea for a stream actually, because I feel like this is more interactive because you can ask questions and there's so much stuff that might be unclear. Greenbrier Studio says none of those have a board footprint. True. Yeah, true. That's also an advantage of the system one that I just used, because that one has a footprint for the PCB. Peter says it makes the schematic less flexible when you build function blocks. Yeah, but I mean in our case we are only going to ground like all the other inputs, so I think it's fine. Yeah, it's the 74HC14. That's the chip, right? So that one won't substitute for the 4106. Okay, so let's go back in here and let's get going with this. So the first thing that we need to do, of course, is we need to power our chip, because right now you can see the VSS and the VDD, which is the ground and the positive connectors, they are unconnected. And for the chip to work at all, we need to power it, basically. Now, how do we do that? Well, it's very simple. For ground, we simply go here, again, into the EELib tab, and then we can just pick up this ground symbol, and we can just place it somewhere where it will look nice, maybe here. I don't want to put it here because to my eyes, it looks a bit squished. So maybe, I don't know, here. It's a matter of taste, whatever. Okay, and then obviously, as you can see, there is no connection between these pins. So how do we solve that? It's very simple. We go into our wiring tools, and here, now highlighted in blue, you can see there is a tool called wire. You can also just push W on your keyboard, and once you select this, you can connect points via a wire. And you can already see, like, when I'm moving towards the end of a connector, you see this dot, which kind of indicates that you can make a connection there. So in our case, we want to connect the ground symbol with the VSS pin. So all we have to do is we have to click on this ground symbol, like where the dot appears. Once, you click once, you don't drag, you just click. And then from here, you can basically just move your cursor and the wire will follow. And as far as I can see, like all other tools do it the same way. So this is just how it works. Okay, and then what we do is we just move towards the VSS pin until the dot appears, and we know that we can make a connection there. And then once we click, the wire disappears. You can see now that we have this nice green connection here. And yeah, so now this VSS pin is connected to ground, which is great. And now we need to do basically the same thing for the VDD pin, for pin 14, but we need to connect that one to the positive rail. And now you might be confused because all we have here is something that says plus 5 volts. But that's not a problem at all, because we can still select it. We can still place it here. Now let me get this correct so that it's symmetrical. Boom. And yeah, now it says plus 5 volts, but what we can do is we can go in here, we can select this label, and then if we double click, we like this kind of edit window opens up, and we can just replace this with plus 12 volts. Now it's 12 volts. I mean, the software like doesn't really care what you put there. There's just the label for how it's going to be called. Plus 12 volts in our case. Also, if you want to do a system with 15 volts for whatever reason, put that in there, 9 volts, whatever. But just keep it consistent. I think otherwise it's confusing. Okay, so in my case, we're going to do plus 12. And then we also need to wire this up. Sorry, my English is terrible today. We need to wire this up to the VDD pin. So same thing, click on the dot, navigate to the pin, see the dot, click again, and I messed it up, fuck. Okay, what you can always do, of course, is a Command Z. So if you do Command Z, it disappears. So let me try again. We move here, we click, and it worked. Okay, so now we have a connection here to plus 12 volts, which is nice. Okay, so far so good. And now comes the kind of wasteful part. The problem with my VCO design basically is, since I'm using this chip, which has 6 inverters, but my design is only using 1 of them, we are going to have to waste 5 of them. We are going to have to disable 5 of them, which, yeah, it is wasteful. On the flip side, the chip is dirt cheap, so I don't feel too bad about it. And yes, some people have kind of suggested that you could also replace this with another op amp that you kind of configure as a Schmidt trigger inverter. But for simplicity's sake, and just, you know, I often explain this layout to beginners, I feel like it's easier if we just use this chip, which does all the configuration for us. But the trade-off is that we have to disable 5 of these inverters. So let's go ahead and do that. Now the question is how? And it's very simple. You disable the unused inverters by connecting the inputs to ground. So here you can see all the pins that are labeled with an I are inputs. All the pins labeled with an O are outputs. And so for all but one, we will now have to connect the input pins to ground. And we do that the exact same way that we just wired up the other connectors. So we go to the pin, we click on the dot, we move to ground, wherever that is. Boom. And here you can see, like, whenever the green lines cross basically and you have a connection there, you see this big red dot. This just indicates that this green line and this green line, they kind of join up and they are connected. You could potentially also have 2 green lines cross and they are not connected. Then you wouldn't have the red dot, which happens like whenever I can just show you, when I start dragging a line from here and I just go somewhere here and I finish it there, then you can see there's no red dot because I didn't specifically click here to create that connection. So these, this line and this line, they are not connected now. Okay, cool. So now we have this input grounded, and now we will basically just continue in this manner. And I've kind of determined already that I want to use this inverter up here for our oscillator, and all others I will ground. So this one goes to ground. And then on the other side, will I use another ground? Yeah, I think I will just use another ground flag. I mean, it's just aesthetics, it doesn't matter. Let's put this here, boom. And then I will just, again, pick all the input pins and I will route them to the ground connector. Boom. Okay, so now the chip is properly prepared and we can actually start building our oscillator. And the question is, how do we do that? And this is kind of bugging me that this thing is not centered. So let me quickly do that. Was it centered? No, I think no, it's centered. Boom. Okay, so now we have our Schmidt trigger that we're going to use, which is this one. And now the first thing that we need to do is we need to connect, or maybe I will just switch to the to this view quickly. So we have this Schmidt trigger inverter set up. It's already powered. So all we need to do now is we need to bring in these 3 other components. Oh, I just see in the chat. Yeah, I need to mark the outputs as not connected. Let me quickly do that. So let's jump in here again. And also the software will actually complain in the end because there are now some pins that are just simply not connected, but we haven't declared them as not being connected. So what we should do, or what we actually need to do, otherwise the software will complain, is we need to use this tool from the wiring tools, which is just called the no connect flag. We need to select this, and we need to attach these basically to every output that we will not be using. So this one, this one, this one down here, this one over here, and also that one. Okay, and now the software knows that these are kind of left unconnected intentionally. Like we didn't intend to connect anything there, and now the software knows, it won't complain, and everything will be fine. Thank you, Peter. Okay. So then the next step would be to quickly look at the schematic again. And I'm just realizing I have to turn on the lamp. Give me a second. Just because it's already getting dark and soon you won't be able to see anything. Okay, so when we look at the schematic again, we can see we need to put in the diode here, which is between the output and the input of the Schmidt-Trigger inverter. And then at the input, we need a capacitor that's going to ground. And then I will also put in the transistor already with the emitter connected to ground and the collector connected to the Schmidt-Trigger inverter's input. Okay, so let's do that quickly. For the diode, we can simply use these components in the sidebar, because thankfully down here they have the 1N40-148 diode, which is the one that I use in my design. So perfect, we don't have to kind of sift through the library, we can just pick it out from here. Okay, and as you can see, it is in the wrong orientation. So it's oriented horizontally, but ideally I think for this design we should put it in a vertical orientation. So the question is, how do we do that? And it's actually really simple. So what we do is we use the hand tool. We click on the symbol, and the problem is, like, now my hand is kind of, or my cursor is attached to it. So I will kind of double click on it, and then the cursor doesn't attach to it. And then what you can do is, in the top row up here, you have like some tools to manipulate the symbol basically. And what we can say here is we can say rotate right, and boom, now the diode is rotated, and we can continue. Oh, someone is screaming outside again. Okay, so we can use our diode to kind of go on with our layout. Okay, so I will simply place this over here. Like, I'm quite unsure like how I want to actually go about this. Maybe we'll put it here. No. Also it's the wrong way around, because it has to go from the output to the input. Right now it's oriented in a way that it kind of looks like it's supposed to go from input to output. So we will need to rotate this thing 180 degrees, and now it's correct. Okay, and now just what I'm thinking is we are going to use the input pin much more than the output pin, because the output pin just needs to be connected to our diode, and the input pin is kind of where all the other stuff goes. So the capacitor, the transistor, and also the buffer in the end that we use to buffer the signal. So I will kind of try to build our layout with that in mind. So I will first place the diode here, and then I will wire this side of our diode to the Schmidt-Trigger inverter's output, like this. And then I will wire the other end of our diode to the input over here. And now we have kind of recreated the first thing in a schematic. It's not super pretty, but I think it will do for the moment. And of course, when you build this yourself, you're free to make it more pretty. Cool. Now, one thing that in the case of this diode, we actually don't need to check. But then again, whenever you're using something in this tool from the sidebar, what you should check is you should check the footprint of the component. And you can do that by, again, double clicking on the component. And then here in the sidebar, you will find a heading called custom attributes. And below that, you have several kind of properties, but the main important part here is the thing called footprint. And if you click into this text field, which is kind of counterintuitive, but if you do that, if you click in here, then what will happen is it will take you through to the footprint manager. And what this is basically it kind of shows you on the left side here, the left picture shows you the symbol in the schematic that we see now that we're building the schematic. And then on the right side, we see kind of the footprint, or kind of the way that it is going to be, or the space is going to be represented on the PCB in the end. And this is important because you need to make sure that these footprints kind of match the components that you will be using. And that is especially important because, and there was like some controversy about this in the chat at the beginning, there's basically two main, I don't know if you can call them styles, but ways that components are made. The first one is called through-hole components, and the other one is called surface mount components or surface mount technology. And the difference is that through-hole components, they have like long leads, and you stick the leads into holes and then you solder them down from the other side. So if you've ever built anything with a strip board, on strip board you can only use through-hole components. These are like the traditional, like the big ones. SMD, on the other hand, are very small. They don't have leads, and you solder them onto a surface. Like you don't stick legs through holes, but instead you solder them to the board, and that allows for much more like compact layouts. You can use both sides of a PCB and so on and so on. But here what we are going to do is we're going to do through hole, simply because there's also some controversy around that, but like some people say that soldering SMD is not harder than through hole. But for me, I've started out with through hole. When I build stuff on breadboard, I use through hole components, and I like the continuity. I like to use them, and for me it just seems more approachable, and that's why I do through hole. Maybe someday I will also check out the surface mount stuff, but for now, through hole is for me the way to go. And that means that for now you will have to go along with me on this here. Okay. And so then when we check out these footprints, we need to make sure that the footprints are actually for through-hole components. And the good thing about the diode here in the software is that this footprint is already for through-hole components. You can see this because these round spots, they have like the black dots in the middle. That means here that there's going to be a hole there. And you can also, if you want to be sure, you can down here, you can click on pad size, and then you can choose like whichever format you like. I'm European, so I use millimeters, and then down here you can kind of see how big the footprint is. And so this kind of, you can see it up here. It's very small. It's labeled as A1. And it kind of shows you how far are the holes apart. And in this case, it's 8 millimeters. And a through-hole diode, I think the body is just like 4 millimeters long. So this is plenty of space. This footprint works well with these standard diodes. So in this case, we can just keep using this. Don't worry about it. It's going to work. So this is fine. Okay, so the next thing that we need to add in, let me quickly jump back to the schematic, is we need to add in this capacitor right here. Okay. Whoops. Started my code editor, I'm sorry. Okay, so, and with the capacitors, again, we're in luck. There are capacitors here in this like small little library. And if you remember from the video and also from the schematic, we need to use a non-polarized capacitor. And we are going to use this symbol simply because I'm so used to it. You could also use this one, but yeah, let's go with this. So we will drop this into our schematic, and we have the same trouble as before. The orientation is wrong, so we highlight it, we rotate it to the side, and then we, and then we place it maybe here. I think this looks okay. We wire one side up to, we wire one side up to the diode and also to the Schmidt trigger inverter's input here. And we wire the other side up to ground. And I think I'm going to use another ground flag. I'm not going to route it to this ground flag, simply because I don't like that. So I'll just do it this way. Boom. And then what we should also do is we should adjust the value here. So right now it is set to 0.1 micro farad. I don't know how you say this. But it needs to be I can show you on the schematic again. You can see here that it needs to be a 2.2 nanofarad one. Okay, so we jump back in here and then we say highlight this, double click on it, which again opens the editor, and we can simply say this is supposed to be a 2n2, which is just a fancy way to write 2.2n. I want to be fancy, so I will put it in like this, 2n2. Okay, this is in. And then the next thing will be our transistor, first, before we do that, let's again check the footprint. So I will again highlight this component. I will go into the custom attributes section over here. I will click on the footprint. And there you can see something unpleasant, or not unpleasant, but unfortunate. You can see that this is obviously a SMD footprint because it's super tiny. You can see it's just 1.4 millimeters apart, and this won't work with our through-hole components. So we will have to change this footprint to something that we can actually use. Now, how do we do that? Well, you can see here that there is a search bar here where you can just type something in. Now you need to kind of know what you're looking for. So in my case, what I want to use is I want to use foil capacitors. Like you often see these in my videos, like these little colorful, boxy little things. And so what I will type in is I will type in foil capacitor. And then another thing that I will type in is, I don't know if there's actually an English expression, but in Germany, I don't know if there's an equivalent English expression. In Germany, we say Rastermaß, and then we kind of say how big it's supposed to be. And the Rastermaß is basically just, if you take a strip board, for example, or a breadboard, it means like how many holes it covers. So Rastermaß 5, for example, is a capacitor that kind of spans like 5 holes, which I find to be like a good size to work with, which is why I put this in here. And I just shortened this to RM5. And then I press enter. And then we can see that in the system one, there is just rubbish here. Like, trust me, I've already checked all of this. So what I will do is I will go to user contributed. And here we can see the top one, for example, is very nice. I've used this in the past. It's called RM5 foil cap. The measurements work out perfectly. Like I said, they span like five holes on breadboard or on a strip board, and they fit nicely on the PCB, and that's why I use this one. Okay, so what I will do is I will simply double click on this. You can see this little information thing coming up here saying that updating was successful. And now we don't need to worry about it anymore. Now we know that this capacitor has the correct through-hole style footprint associated with it. So this is fine. Okay, so going back to our schematic here, we can see the next thing we need to do is we need to put in this transistor and then also this one. So I think I want to speed it up a little bit because you know, making the schematic from this point on should be easy to follow. Okay, so we will go in here. I can already see it's not the transistor that I'm looking for. This is the 2N3904, but I want to use the BC548. So I'll look for this, and we are in luck because we have this in the system library again. So this one seems to be okay. So what we will do is we will pick this one up, we will place it here, and just like before, we will wire this up. We will connect the collector to our capacitor. We will connect the emitter straight to ground. And then from here on, oh, whoops, I'm not in the software. Let me go in the software. Okay, so here you can see what I've done. You know, I've picked up the transistor from the library, and then I've wired it up. And then the next step would be that we need to pick up the next transistor, which is going to be a BC558, which is the PNP equivalent. And if we are lucky, then this should also be in here. It is, but it is a bit ugly. That is unfortunate. So maybe let's go with the user contributed one. You can also mix and match these, like it doesn't really matter. as long as they do have the footprint for the PCB, which some of these don't seem to have, and I would prefer if it looked similar to the other one. These are all a little bit questionable, I would say. No. Yeah, that's the problem with the user contributed parts. They are not uniform and they are not super pretty. But I mean, this is just for demonstrative purposes anyway, so probably you can get away with something that looks a bit different. Okay, so this looks very different, but no matter, it's going to work out anyways. So let's pick this up. And if we look at the schematic again, we can see that we need to turn this around. So the emitter needs to be at the top and the collector needs to be at the bottom. So let's switch back into the software. Boom. So we will need to rotate this. That's actually incorrect. Okay, so in this case, we actually need to mirror it. So here next to the rotation options at the top, you can see my cursor, but here below fabrication and advanced, like here, you can see there's the rotation commands, but there's also flip, horizontal, and vertical. What we need to do is we need to flip this vertical, like this. Okay. Then what we need to do is we need to place this here. We need to place the labeling in an okay way. Okay, so then we wire up the emitter to the NPN's base. We connect the emitter also to the positive rail, but through a 1 mega ohm resistor. So I will switch this to 1 meg. I will quickly wire this up. I will take a voltage source. I will place this up here. And then, as I said before, we need to keep this consistent. I will rename this to plus 12 volts. And then the collector here needs to be connected to minus 12. So what I will do is I will choose minus 5 here, do the same thing, place this in here, wire this up, and then I will change the labeling simply to minus 12. Boom. And we are happy, hopefully. Okay, so let's check again the schematic. The next element, like now all of this is done. The next element that we need to do is this combination of a 1K5 resistor and a 1K precision trimmer. And these go in series to ground. So let's put this in. First, we will take a resistor. We will rotate this. We will adjust the value to 1K5, which we just said. We will drag this somewhere around here. Yeah, that looks okay. And then we need to do the trimmer, which is actually, like technically it's just a potentiometer. So what you need to do is you need to select one of these potentiometers here. You need to place them in here. We also need to rotate this. Boom. And then we simply drag this one, maybe here. It's going to be okay. I'm going to take this horrible tag and I'm going to replace this with a value. So it's going to be 1K. I'm going to call this maybe trim 1. I don't know, doesn't really matter. You can, of course, give them more concise names. But for most parts, I like to stick with the suggestion, you know, R1, R2, C1, D1, you know, diode 1, capacitor 1, and so on and so on. Okay, so first of all, let's wire these up. So we will connect the base to this resistor. We connect this resistor to the trim pot. We will connect the wiper to the third terminal. And then we need to connect this to ground, which we just verified. And wire these guys up, and boom. So this is also done. Now, one thing that you might have noticed that I didn't do is check the footprints for our resistors. And we can do this now. So if I click on this one, again, go to the custom attributes, click on the footprint, and you will see with horror that this is again a SMD part, which is unacceptable. So we need to go for a resistor footprint. Now, I think what we're going to do here is we're going to use, go ahead and use the 1/4 watt resistor type, which I think is the most common. I tend to use different ones that are metal film, and they are smaller, but I get the feeling that people are like having trouble finding those. So for now, let's go with the standard part. So we're going to say resistor, and we're going to say 1/4 of a watt, and we're going to look for that. And again, there's stuff in the system, but I kind of think, that's actually okay. Let's check the size. So they are 11 millimeters. Yeah, I think that's about right. Here's 1/8. That's too small. Let's go. I'm gonna go with these 7. Actually, I don't use the 1/4 watt ones. Let's go with the bigger ones just to be safe. So we'll go with this footprint. Boom. Double click, it will update. Done. Now the good thing is when we go to the next resistor, and again we click on the footprint here, the search is kind of saved, and we can simply say, okay, we want the same footprint. Boom. So it's already highlighted there. Just double click it again, and it's applied to this resistor as well. So then we will check this potentiometer. Same thing, go into the footprint, and we can see there is some weird looking thing here, or at least weird looking for me because I don't use this type of potentiometer. So what I want to do is, and this is something like, I don't know if there are there are like certain standard parts for these eurorack modules. What do I mean by that? Well, simply here, like if you look at this, for example, you can see this is a potentiometer, and this is a kind of special kind, not a special kind, but like a special style of potentiometer. So these are by a brand called Alpha, and the kind of distinguishing factor is that they can sit upright on a PCB. So on this one, for example, you can push them in here, and they kind of slot in, and they are facing upwards, which is not standard. If you look at these ones here, for example, they are kind of in a 90-degree angle, so they're looking this way. So if you were to stick them in here, they would look, like to the side. You could also make that work, but if you want to go with this kind of style of assembly, you should go for these. And what I mean is just these are kind of a eurorack staple. So many manufacturers use these. So that's why I decided to also go for these. And then also there are these little switches that are also a kind of standard. And also these audio jacks, which are called Thonkicons. They also have like a proper name, but they usually go by Thonkicons. And they have the same benefit as the potentiometers, so they can sit upright on your PCB like this, which is just, it's just convenient. I think that's why many people use these. And now my question is there like a standard part for trimmer potentiometers? And I actually don't really know, but probably it's not that important because it's not an interfacing element. So what I will do is I will kind of go for the ones that I usually use, if I can find them. Let's see. So let's simply search for trim pod. And let's first check the system ones. And these all look super weird. I don't like the way they look. So let's check the user library. Yeah, these are the ones that I use. Not these, not these. These ones. Now, to be sure, you should probably, or I should probably test this. So I should measure, but I'm pretty sure that these are the ones that I use. So I am simply going to go for these. So double click it, it updates, and boom, we have our footprint in there. Perfect. Okay, so let me switch back to the breadboard view, not breadboard, schematic view. Okay, so now we have all of this completed. So all that we need to do on this side now is the CV input and the coarse tuning potentiometer. So let's do that. I think we will start out with the coarse tuning potentiometer simply because it's a bit simpler. Okay, so what we need for this is we need to use another potentiometer. So I will select one from the sidebar. I will place it here. I will simply turn it. And the quirky thing about the design is you have to connect this on the one side to the negative rail. So I will connect the negative kind of indicator here. I will rename this to -12 volts. And then on the top, we actually need to connect to ground like this. So wire this up, put this in there, and boom. Now I think I have placed this a bit far to the left, so I will highlight it and I will drag it. This is also, this is a very buggy feature. Like sometimes it doesn't register all the stuff that you highlight, even though it's clearly in the box that you draw. So if you want to be angry about something with this software, it's probably this feature. It's really annoying. Right now it works well, but you know, usually it usually it really doesn't. Okay. So then what I will do, I will put in first the 100K resistor, and then I will put in the 10K thermistor. And let's hope that we can find a thermistor in the system somewhere. But yeah, we'll start out with the resistor. We will connect this thing here. We will put in the proper value, like we do. We will adjust the footprint. So we will call this, we will get another quarter watt resistor footprint. Boom. Save this there. And then we will need to look for a thermistor. It needs to be NTC as opposed to PTC, so negative temperature coefficient instead of positive temperature coefficient. So look for this thing. And this actually looks quite promising. And these don't have footprints. That is not how my thermistors look. That is closer, but very ugly. Yeah. I mean, the value is wrong, but that doesn't matter. Those are SMD. SMD is not for us. Oh, I think I like this one. The footprint looks nice. Okay, so let's go with this one. So we will put this guy in here, and we will wire this guy up. And then, of course, I missed the mark by like one square. Okay, so there you can see I clearly highlighted the thermistor and all the other components, but it kind of just refuses to select this. Maybe there's a good reason. Maybe if someone knows, please. And also, sometimes you just can't drag for some reason. No, this software is very confusing to me. Okay, hopefully I can make it match up. I think here. Of course not. Yeah, you know what? No one cares. So let's just pick up the wire tool, move here, connect it down there, and boom. So this means that our coarse tuning, of course it's in there, let's just call it coarse, is done. And now all we need to do, okay, we already fixed the footprint on this one. We need to fix the footprint on this one. So what I will do here is I will use the alpha, which I just showed you, like this potentiometer, this green one, this vertical one. So if you're looking for this, you can usually just put alpha and 9 millimeter. And normally, if you then go to user contributed, you should find the footprint. Yes, perfect. One thing to kind of note here is, this is more like advanced stuff, but you can see in the PCB footprint here that the two holes in the middle to the side, they're kind of elliptical, they're not round. And with most Chinese manufacturers, this doesn't make a difference. If you want to produce in Europe, more specifically at Isla, then this is important because they will charge you an extra fee and it will take longer to build this. So you may not want to use this footprint. I like the way it looks. That's why I will just use it now. But when you build your own thing, you can exchange it for something that has like a round connector there. Okay. So footprint is in there. Then check the thermistor. We'll go in here and we see that this is probably fine. Yeah, they are super small. So 2.54 millimeters is going to be completely okay. Cool, so this is done. And now the last thing on this side that we need to do, let me quickly check back here, is the CV input. And I'm rushing through this because I want to get done. I want to get the schematic done basically, so we can get to the actual PCB design. Okay, but CV input is a socket, a resistor, and then a thermistor. So let's let us go back in there. Or I just saw a comment by Warpigs. What is the schematic for? I explained this in the beginning. So maybe if you rewind, like I said, I'm trying to crunch this here. Okay, jumping back into the tool. So the first thing that we need is we need a jack socket. So what we can look for here is Thonkicon, which is how they're called like informally. If you look for this and you stay in the user contributed category, you should find some stuff that is going to work pretty well. There was one in particular that I used that looked nice and that worked. Let me try to find this one. No. Oh yeah, I think there's like two different versions. So this is the old version, and they have a new version of this socket. So maybe use the new one if you want to use that. That will make sense. Well, where is it? These all look very, very ugly. No. I think this would do probably. Footprint. I mean, who cares? Like, we're not gonna produce this now anyway. So let's just pick this one. Put it in here. We need to mirror this horizontally. Up here again, you can see now that you should see the tag saying flip horizontal. If I click on that, then boom, it turns around. And now you might be a bit confused what these three connectors are, because usually with these mono connectors you have two. So the pin 2 one. So let me zoom in. This pin 2 is it's called a switched connector. So basically, what happens is you can, like anything that you connect to this one will kind of connect to the first pin whenever there's nothing plugged into the socket. So whenever nothing is plugged in here, then it will kind of default to whatever signal is applied to the second pin. We don't really need to use that. So we can just leave this unconnected. So what I will do is I will pick up the unconnected flag. I will place it here and boom. Then the third connector just needs to be grounded. It's always the same. Just place a ground connection here, connect that thing, and boom, you're done. Then what we'll do is we will place another resistor here. We will again, no, give me a second, I have a better idea. So what we can do is, since this is identical to the stuff on the potentiometer thing here, we can simply, hopefully this works now, we can highlight this. we can do Command C. And then we should be able to do Command V. Come on. Yes, perfect. Sometimes this works, sometimes it doesn't work. If anyone knows why that is, please tell me. It's super weird. Now it worked, which is great. Okay, so we wire this up. Connector 1 goes to the resistor, and then the end here simply connects down there. And now we are almost done. All we need to do now is we need to pick up our signal from here, from the Schmidt-Trigger inverter's input. That's how that works. I can show you again on the schematic. So we now have basically all of this done. All we need to add now is this connection here to this buffer, which is then AC coupled. And then we get to our output amp, and then we send that out to the output socket. So we just need to put in these two op amps, these few resistors, and we're done. Okay, let's start with the buffer. So what we will do here is we will use a chip which is called TL072. And that is 2 op amps on 1 chip. And probably this should be in the system because it's like such a standard, it is such a standard chip. Okay, these have like very ugly footprints for whatever reason. Probably this is also not the right format. So maybe here these are actually better. Yeah, they look okay, I guess. I don't want to waste too much time on this. I hope you guys are up for a bit longer. No, but these are all ugly. Anyway, I'm going to get over myself. Let's just use these. Okay, so now what I did is I selected the first op amp in this chip. So this is basically from this chip, TL072, the first op amp. And I will simply place this, I don't know, somewhere up here. Okay, and then what we need to do is, just like with this chip, we need to power our op amp chip. So the way that we do this is we need to connect this bottom side to the negative supply rail. We need to edit this to be at -12 volts. And then what we do is we add in another one that will sit here. And now the labeling is in the way, which is why I will move it. Of course, move this one here, move the label back, and then rename this to +12 volts. And maybe move this somewhere else entirely. I think he would be okay. Okay, so now we've set up our first op amp. And going back to the schematic, we can see we need to connect this as a buffer. So the non-inverting input goes to our Schmidt-Trigger inverter's input, and the inverting input needs to connect to the output, and that way we configure it as a buffer. So far, so easy. Okay, so we simply connect the non-inverting input to this point. You know, and all of this is connected to the Schmidt-Trigger inverter's input, so this is fine. And then on the other end of the spectrum, we take this inverting input and we go through the text and we go to the output. And now this thing is set up as a buffer. Cool. The next thing that we need to do is we need to use a non-polarized capacitor followed by a resistor to ground, which should be a piece of cake now because we are already almost experts at this. So let me pick out a capacitor. Let me put it in series here. I will wire it up and I will adjust the value. So this needs to be a 1 microfarad capacitor. We will pick out a resistor. We will turn that to the side. We will put this in here. And this goes to ground, like that. Then we need to wire all of this up. we need to adjust the value. We need to adjust the footprint. Maybe I should have done this all in the end, you know, when I could have just picked the same footprint for all of the resistors, but it's too late now anyway. So, and I kind of remembered what the name was. Foil capacitor RM5. That's how I was looking for it, and I think it's done the first hit. RM5 foil cap, exactly. Boom. Put that thing in there. Cool. And for the op amp, obviously we already have our footprint here, which is fine. Cool. Going back to the breadboard, and now there's not much left, so we need to add in the second op amp from the TL072. And with these resistors, we need to configure this as an op amp with gain. So what this does is kind of blows up the signal to be 10 volts peak to peak, which is like a modular standard basically. Okay, so then the question is, how do we do that? How do we do that? We go in here, we go into our library, and we still have the first op amp connected. Sorry, selected. So now we can simply select the second one. We double click, we put this guy in here. And I'm actually not sure if you have to put in the power connectors again. I will just do it just to be thorough. So I'll put in the positive, the negative rail. I think someone put in the chat that I can just copy and paste the resistors, which is probably a good idea. So I will do this now. So I'll wire this here up to the non-inverting terminal. And then I will use another wiring tool, and I will move this here. How did I do it there? Okay. So let us simply go here. And then I will pick out this resistor here, which I can select. Perfect. Copy paste it. Okay, and now this should have the footprint right. Yes, it has the correct footprint. Perfect. This one needs to connect to ground, which I will do uglily like this. So, boom. And this needs to be a 47K, which you can't see, but I can see on the schematic, so trust me that this is correct. We will take another resistor, so take this one. And now it's an instance where copy paste doesn't work. Still doesn't work, and now for some reason it works. I just click around madly and then it does work. So I don't know what's going on there. Take this, and we need to place this in here. We need to connect these guys and these guys. And we need to adjust the value. This needs to be 100K. And I think that should nearly be it. Now the last thing that we need to do, if we go back to the schematic, is we need to put in the 1K here, which just protects the op-amp's output basically from being shorted and dying. And then we need to add in one last jack socket. And then we can get to PCB designing actually. Okay, so let me copy paste this resistor. I'll put it down here. I'll connect this to the output, and I will give this a proper value, so 1K. And then what we should do again is we should connect, we should copy this jack socket over here. We'll paste it in here. We will need to mirror it. And then all we have to do is we have to deal with it the same way we did with the other one. So pin 2 gets a no connection flag. Pin 3 gets connected to ground, like that, boom. And this resistor connects to this jack socket. We name it to output. and we will call this the CVN. Whoops, sorry. And now we are done. Now we're not done yet. We will have to do one more thing. But for the core circuit, we are actually done. Hooray. Okay, so quick question time. I will check the chat. Also, if you have any questions just regarding this process of putting the schematic together, then feel free to fire anything off. Let me quickly see what's going on here. So I won't go back too far. So the parts hitboxes seem to be a component of their schematic symbol, and some people design them in such a way that all the text needs to be inside the selection. Yeah, that's what I kind of felt like, that you also need to have the text in there, which is confusing and it's annoying. And yeah, apparently it's inconsistent. So yeah, it's weird. I don't know how this is in KiCad. Maybe you can tell me how that works there. What else? You can use all 6 Schmidt trigger inverters, right? Yes, you can use all of them. Theoretically, you can build a kind of 6 oscillator circuit with this, no problem. But for this one, it's just small, so I just chose to deactivate all the ones we don't use. Is EasyEDA worth the effort? It's proprietary for KiCad. Is this so much more complicated? Martin, I wouldn't say it's worth the effort. It's just what I started with, what I'm most comfortable with. Also, it's in the browser, so I feel like it's accessible to complete newcomers. But yeah, I also already told people that I would kind of urge them to go with KiCad. I think that's the better choice in the end. What else? 1K not needed as TL072 is shortcut protected. That's true. I've also read that it's not needed. Still, I'm uncertain. Like I don't want to leave it out completely, simply because I see it in so many like professional synth designs. So that's why I kind of choose to kind of adhere to the standard. But if you say that we really don't need it, then maybe that would be a good thing to omit. Anyways. Let's go on. What else do we have? We new people need this, brother. That's good to hear. Is that op-amp connection drive state wrong? Because R6 is not between the connection and ground, but between the connection and the inverting input. Let me quickly check R6. I will go to R6. This one. Yes, it's actually incorrect. You are completely right. So this thing needs to go, this thing needs to go, and this guy needs to go here. Thank you for picking up on that. That would have been a disaster. So move this in here. I think I want to go up here a bit because otherwise it just looks super ugly. Boom. Okay, let's quickly save this. And now hopefully everything should be dandy there. Thanks for the heads up, definitely. Thank you. So could it be that the 47K is positioned different in the drawing? Yeah, I already fixed this. Thank you. James says, I mentioned it earlier in case you missed it. When selecting left to right and right to left, selecting works differently. You mean when drawing a box? I'm not sure. Peter says, you missed some hints about using keys for rotating parts. Maybe, yeah, probably like shortcuts are always a heaven sent. So yeah. James says, left to right, you have to have box cover all components for them to be selected. Right to left, you can draw box partially over. Okay, that's that's quite cryptic, but good to know. Thank you. And then Juice, Lego, and Electronics says you can use a 4069. No, you can't. That is not a Schmidt trigger inverter. It is an inverter, but it's kind of an analog inverter. Like it doesn't have like these thresholds, so you can't substitute them. Can't substitute them. You could make it work, but it's a different kind of chip. I wouldn't recommend going through the hassle there. Okay, so let's go back in here. So like I said, we are done with the core schematic. But one thing that we do need to do is we need to worry about how we power our circuit, because right now we only, you know, we've kind of indicated, okay, this should go to ground, this should go to minus, this should go to plus, but we haven't specified like how we're going to connect our circuit to a power supply. So we need to tell the software how we're going to do this. And the way that we are going to do this is, again, a very standard way for eurorack. Let me quickly see where I put it. Here. So what we will use is we'll use these pin headers, which are like in the beginning I thought like these are like some proprietary thing, but these are extremely super common. So chances are your electronics store around the corner will have these. They are just a very common part. These headers have 10 pins, and it's really just the pins coming out on the back there, and you can just solder them into the PCB. And they also have, which is nice, they have like this kind of gap, which makes sure that when you take the connector that belongs to it, like these are the eurorack power cables that you use, you can see that they have like this little notch up there. And this kind of ensures that you can only plug them in the right way, only like this. Because if you try to do it the other way around, then this will just mechanically not work, which is a good thing, I think. And so the first thing that we're going to do now is we're going to look for this component in the editor. Like I said, because it's a generic component, we won't have any trouble finding that. Okay, so let's switch over to the library, and what we can do, actually, I don't know, maybe we can look for header and 10. Maybe this will already give us what we're looking for. No, I think that's not correct. So what we can do definitely is we can search for eurorack 10. And then if you're on user contributed, this should give you the proper one, right? So these look exactly identical, so I guess we can just use this one. Okay, so double click on it, and again we get the symbol into our software or into our schematic here, and we can just plop this down basically anywhere. So I will put this in here, and now the question is like, how do these connectors actually work? And well, the way the pins are connected is a bit counterintuitive, but it also kind of makes sense. So how it works is these two pins down here, so pins 1 and 2, they are supposed to be connected to minus 12 volts, or rather, if you connect this to the power supply, these two pins will carry minus 12 volts. Then these two pins up here, so 10 and 9, they will carry plus 12 volts. And all the remaining pins, so 8 through 3, they all carry ground. And as far as I understand this, the thing is that the pins on the header are like rather flimsy and small. And that's why we kind of use multiple pins for the same purpose. So 2 for plus 12 volts, 2 for minus, and the rest for ground. That's how I understood, like to kind of ensure that we have enough bandwidth, like to carry the current, we use multiple pins. And for us, this basically just means that we need to connect these accordingly. So what I always do first is I connect all the ground pins together. So connect these. On the other side, pins 7 and 5, 5 and 3. And then we need to go around the thing here, and we need to go back here, and we need to make sure that these are also connected. Okay, so now all the ground pins are connected together, but we still need to tell the software that this is basically where we get ground from. And the way we do that is a bit counterintuitive. Like, to me, it was a bit counterintuitive, but the way you do this is you simply select the ground flag again. So the same thing that you used like for all the other parts in a circuit where we use ground. So you use this flag, and you just connect it to your ground pins on here. And what that means is that now like every spot that has this ground flag will be connected together. So this one is connected with this one, is connected with this one. Whoops, I didn't mean to do that. Let me reverse. Right, so these are all connected together, and that means that they are also connected to our power header, which means that they are connected to the power supply, which means all is dandy and well. Okay, so then the next thing that we need to do is we first need to connect the minus pins together, obviously, because they need to be, they carry the same signal. Same goes for the positive supply. Boom. And now you might be tempted to just simply, here select the plus and minus 12 volts flags and just simply connect them. And while you could do that, and while that would work, there are a few things that you should do. And you probably, there are a lot of discussions about this online. A lot of people are asking, how do I do this properly? And so I will simply show you how I do it. This is probably not the, how do you say this, end all be all solution. But, give me a second. There are two things that you should do. The first one is reverse polarity protection, and the other one is decoupling. Now, first, what is reverse polarity protection? It's very simple. It's to protect the device when the user plugs in the power connector or he wires up the power supply the wrong way. So he kind of interchanges plus and minus 12 volts. Now, why is that a problem? Because most chips, like the op-amp chip and also the Schmidt trigger chip, they really don't like it when they get reverse polarity, like when they get the power in the wrong direction. Usually they will go up in smoke. So we want to kind of prevent this. Now, as you saw with this type of connector, you already have the mechanical protection here. So this already kind of keeps the user from plugging it in the wrong way, but still there could go, like something could go wrong down the line. Maybe the power supply is also self-built, and there you have it like wrongly wired up, whatever. Or maybe you are very crazy and you just push it in with force or something. We need to kind of take that into account, and that's why we do reverse polarity protection also in our circuit. And the question is, how do we do that? Well, there's a lot of different approaches. People do it this way, that way. The simplest way to do it would be to simply use diodes. Diodes basically, they allow current to only go in one direction. If you try to have a current flow in the other direction, then they will simply block. Now there's a small problem here. A diode will drop voltage. So if you simply use a normal like 4148 diode, then they will drop about like 600 millivolts. So instead of 12 volts from the power supply, you would only get about 11.4 volts. Which, I mean, it doesn't really matter for our circuit here, but usually you want to have as much headroom as possible. So you want to have as much voltage from your power supply. You don't want to waste anything, which is why there is a better choice of diode, which is called the Schottky diode. Schottky diodes just drop less voltage. They don't drop 600 millivolts. I'm not quite sure. I think it's like in the range between 300 and 400 is what they drop. So you save some voltage for your circuit. That's why people use those. And that's why we are also going to use those here. So we are going to go here. We're going to select the diodes. And I hope... No, these are not Schottky diodes. So we will go into the library, and I will simply search for Schottky, and hopefully we will find something. No, that's not correct. Let's go into the system one. These are ugly footprints. These are very ugly footprints. Let's go to the user-generated stuff. These all don't have footprints. This is also exceptionally ugly. I think this seems okay. Okay, so for the positive rail, it needs to go in this direction, right? Because the electricity flows from here into our circuit, so it needs to go in this direction, which is why I oriented the diode in this way. So I will put this guy in here, and I will wire this up to our connector. And let's quickly check the footprint to see if this is if this works. But yeah, it's 7 millimeters. I think this seems okay. So let's just go with this one. I will then copy paste this one, which again doesn't work, and now it works. Whoops, and now it just went away. This software is really strange. Okay, flip this around because, just like I explained, from the positive rail, the power goes this way into our circuit, and with the negative rail, the power basically comes from our circuit. It goes through the diode and goes into the power connector, which is why we need to orient it this way. So try to make this nice and even. Put this here, wire this up to our negative rail. Okay, now we have our reverse polarity protection, which is already great. Boom. And now the second thing that we want to do is we want to do decoupling. Now, what is decoupling? I think I've never talked about this in my videos. So decoupling, very simply, is you want to protect your chips from noise that might be present on your power supply rails. So what could happen is that kind of other modules, they draw power from your power supply and they kind of switch like very rapidly. For example, this oscillator will kind of switch back and forth between high and low states like constantly. So it will kind of quickly change the demands it makes on the power supply, which will mean that the power supply, if it is not like a really, really well-built one, it will kind of pick up that noise and it will deliver it to all the other modules. This is something that will invariably probably happen, which is why you need to kind of prepare for that. And the way that you do that is you simply use small ceramic capacitors that you place as close to the pins, to the chip's power pins as possible. And these capacitors will basically act as little like power reservoirs. So whenever the power supply kind of drops in voltage very quickly, which is what noise is, it's just that the power supply, the voltage of the power supply fluctuates quickly. So whenever that happens, these capacitors that we will place like very close to the power pins of the chips, they will kind of act as a buffer. So they will kind of compensate for these quick fluctuations, and which will kind of prevent that noise from entering our chips. And so this noise will hopefully not be present on our output. That's how that works. And the way that we can do this in here is actually very simple. I think we might actually need a bit more space. So what I will do is I will pick this up and I will drag this a bit down, just simply to give us a bit more space to operate with. Connect this here, and boom, we're done. Okay, and if we look again at our schematic, what we have here, we have two chips essentially. So first we have this 4106 chip, and then we also have this TL072 chip. Now the thing is, this chip is connected to plus 12 volts and ground. So we just need one single decoupling capacitor for this chip. So we need one decoupling capacitor that is connected between the positive power pin and the ground pin. For the TL072, we actually have, like, these are connected to the positive power rail and also to the negative power rail. And I think you could also use a single capacitor that is connected between the positive and the negative rail. But from what I've read, the more effective strategy is to use two decoupling capacitors. So one that is connecting between the negative input pin here and ground, and one that is connecting between the positive input pin and ground. So two decoupling capacitors for op-amps. What I've heard is like the way to go. Correct me if I'm wrong. Okay. This might sound very complicated, but all we have to do is we have to put in 3 capacitors here, basically. So let me simply put in one here. Oh, give me a second. I'm going to copy paste these as someone suggested. I think that's... well, no. We're actually going to use a different footprint. So no, it's actually okay to use these ones. So select this one, turn it to the right, go into the footprints. We want a ceramic cap footprint. I'm going to go to user contributed. And these are all very ugly. I think, is this the one I'm using? No. This one. This might be it, actually. I mean, this is super small. This is basically, I think it's just like two holes wide, but these ceramic caps, they're like super tiny, so I think this is the proper one to use. So we will use this footprint. Now the size is already correct, but let's be explicit. Let's say these are 100 nanofarad. So this is the value that I use for decoupling caps. This is the values that I see recommended the most. I'm not sure if it is the best for our application, but so far I've been using these. I didn't have any problems. That's why I keep using these. If you can tell me that these are not the right choice, please feel free to put it in the comments, and I'm happy to change this to a different value. But okay, so this is going to be the decoupling cap for the 4106 chip. So I will connect this to the positive rail, and I will also connect this to ground. Because remember, this decoupling cap needs to connect between the power supply pin here and the ground pin. So power and ground. Then we will copy paste this guy, and we will need another one that is also connected between the positive rail and the ground rail, because this is for the TL072, for the op-amp chip. It's going, between the power connector and the ground connector. And then we will copy paste this thing again. And this time we will connect this between the ground and the negative rail. So this one goes to the negative rail. And with this, we should probably be done. The last thing we need to do is we need to connect this top rail here to our power rail flag, basically. So if I put this in here, then now the system knows that all the other instances of this plus 12 volts flag, so here and wherever else that is, needs to be connected to here, which is connected to the power connector. So it's all good there. We need to do the same thing for the negative flag. So boom, put this guy down here, make this minus 12. And then one final thing that I like to do, that I saw someone else do, I think, in a tutorial, so it's not my idea, is to kind of show that this is not part of the main circuit. And the way that I do that is I select this tool here on the side, this rectangle tool, and I simply draw a rectangle around this section, basically, boom. And then I like to select this, and I like to say dashed here, just because it looks nicer. And now I kind of feel like, it's clear that this is not part of the main functionality. It's not part of the main circuit. So that works out quite nicely. Okay, and with this, we are actually done with the schematic part. It took longer than I expected. I hope you're still on board with this. I will quickly go into the chat and see if anyone has anything to add here. So, scrolling up a bit. Okay, so I see that you have been talking about Dupfer. So DevJog is asking, why aren't the pin connections made rotationally symmetrical? They would save an accident plugging the connector in back and front. I can't tell you. It's actually a standard that has been kind of set. And yeah, I see that you're already talking about this. This kind of just the way the Dupfer kind of decided to do it. So this is how it's done. I think it makes sense to kind of obey to those standards to make it compatible. That doesn't mean it's the best way to do it, but that's just how it's been done. Let's go on. Yes, the 16-pin one is for 5 volts, which we don't need on the circuit. We only need plus, minus 12 and ground. Okay, let's continue. What do you call those header pins you can cut to smaller sizes? I think those are called, no, they're not DuPont headers. Someone else help me out here. I don't know. Pin head is breakable. Yeah, that might be it. T-Killer says, the funny thing is that Dupfer discourages people from using box headers because it forces people to put the cables in a certain way, which could be wrong according to them. I prefer the box ones just because it prevents idiots from doing idiotic things, which I am also an idiot. So I appreciate the kind of guidance there. Josh says, screwed up my power supply recently. Most of the chips in my modules fried. The wonders of being a noob. Yeah, that's why we added in the protection diodes. I don't know if you saw. Yeah, but that's what that is for. Let's go on. I assume that you already did this. I think it's a really good practice to use chip sockets, which we're going to use now in the layout. We can't actually use those in the layout, but I encourage everyone to use chip sockets because then you can simply pull out the chips, put in new chips in case anything goes wrong, they break, whatever. I think chip sockets are the way to go. Super helpful. David says, reverse polarity MOSFET protection have lower voltage drop for protection. That's true. If you use MOSFETs, you can also do some things with fuses. Again, for this circuit, the voltage drop is not significant. It's not important, so we can gladly live with that. It's fine. Warpig says, for bulk decoupling, I usually use something in the 10 to 20 UF range. Are you talking about? Not quite sure what you're talking about there, because I mean the size does matter, like in regards to which kind of frequencies they filter. So smaller caps will filter out more high frequency noise, bigger caps will filter out more low frequency noise. So it kind of depends on what you're trying to battle. So if you have a lot of like ground hum, which is like I think 50 or 60 hertz, you should go for bigger caps. In our case, it's probably only going to be crosstalk between the modules. And the stuff that's going to be like really annoying is the high frequency stuff. So that's why I go with the small ones. So droning brightness says, kind of basic question. How are plus 12 and minus 12 not interacting in that power supply schematic? You mean, are you talking about the green lines that are overlapping? Maybe you might be talking about that. I talked about this in the beginning. So you can see here, only where there are red dots are lines interconnected. So if like down here, lines cross, but there is no red dot, these lines do not connect to each other. If you meant that. So this is the thing here. Otherwise, you would have to clarify what you meant. Raketensessel says, I got here a little late. Maybe you can talk a little about your progress on the diode ladder filter. I will do that in a minute. I think first we're going to assemble the PCB layout, which is going to be way quicker than this circuit diagram. So Ju says, when comes the video with the VCA? I will also talk about that in a bit. I made good progress this weekend, so I hope very soon. DevJog, so the PCB layout part is going to be in another stream. No, we're going to do this now. Don't run away. We're going to do this now. T-Killer says, I agree with Warpig's. Bulk capacitors near the 10-pin header is highly recommended. Again, like, I'm not sure if we're talking about the same thing here. I think if you use one big one, maybe I'm wrong, but I think it doesn't filter out high frequencies. Correct me if I'm wrong. Victor says, the pin layout on the power connector is actually pretty convenient when making power rails from strip board, since it can just be aligned with the strips on the board. I didn't know. I never used those 10-pin headers for my strip board layouts, but yeah, good tip. The bypass capacitor should be close to the chips. True, but that's only relevant for the PCB layout in the end. Lucas says, the stream opens a new world for me. Thank you so much. Very glad that it helps. I'm a bit worried that I'm spending too much time on the circuit stuff, but making the schematic is integral to actually building the PCB layout. So I think it's worth to spend time on this. T-Killer says, both 100 nanofarads and bulk capacitor is recommended. Yeah, true. I hope you will forgive me if I leave this out for now, just for the sake of time. But yes, if you build this, probably it's really good practice to also add the like 10, I think I'm using like 10 microfarad caps near the power header. What else? DevJog says, of course I'm sticking around, great. Decoupling caps should be placed on board as close to the component as possible. Yes, but on the schematic it doesn't, like on the schematic you put it anywhere. Of course on the actual PCB layout we need to put this as close to the actual components as possible. You're completely right about that. But yeah, let's quickly run through this, see if it all works. So we have our oscillator core here, which seems to be set up nicely. I have the transistor, which is controlling the frequency. We have the emitter follower with the PNP transistor, which is followed by our kind of tuning circuit. Then we have the two CV inputs, which seem to be set up correctly. We have our buffer, we have our AC coupling, we have our amplifier that will blow things up to the 10 volts peak-to-peak standard level, and then the output, and then it's done. This seems to be good. The power header, here everything also seems to be connected correctly. We have our Schottky diodes, which are protecting from reverse polarity. We have our decoupling caps. So we should be good. Okay. So then, of course, you need to save. Always save your stuff. And then the next thing that we do is we go here to the design. I don't know what that is. Design dropdown. And we say convert schematic to PCB. And you can see that that the software immediately went there. Sometimes it won't let you go there immediately. Sometimes, for example, if you forgot to put in these no connection flags, you know, these green X's that we put, for example, on all the pins that we don't use, if you don't place them, the software will refuse to go to this view, and it will tell you, hey, please either connect those pins or put the flag there. But either way, I'm not letting you go into the actual editor. So you would have to do that. And then also the software is running. Oh no, that's actually next up. Yeah, that's what that's doing. And also it will tell you if if a net is incomplete. So if you have parts of your circuit that are not connected to anything else in your circuit, it will also tell you, hey, there's no connection here. But in our case, everything seems to be okay. So now we are prompted with this new view where we are supposed to kind of choose the dimensions for our PCB. And we can see here that it already suggested something. So it already put in like some parameters, and now we are kind of asked to verify this. Okay, and the first thing we have to kind of check here is for the copper layers. Now, for our purposes, I'm very sure that 2 is completely okay, so we can stay at 2 layers. And then we need to choose the board outline style. So you could do something like circular or round rectangular. Fancy, but we are just going to go with rectangular. And then we need to choose the dimensions here. And this is where it gets like a little bit tricky, because of course, when we choose the dimensions, we need to think about our module in the end. So we need to think about how big should our module actually be. And this is not a trivial question, because if we want to kind of adhere to the eurorack standard, we need to check their kind of design, their kind of design specifications. And I found the best place to do that is actually on the Dopfer website. I hope you can see this. Yes, you should be able to see this. So if you simply, you could either just take this link, or you could just search for this here, for A100 construction details. So what this is kind of the documentation for the format of eurorack modules. And the stuff that's actually interesting here is basically this picture here, and then also this table. So we can see we can find 2 important informations here, roughly. So the first one is how tall are the modules, are the eurorack modules. So you can see here that they are 128.5 centimeters high, and there's some weirdness going on, I think. So like actually the height is 133.4 millimeters, but then they kind of explain here that they need to leave some space for the rim of the mounting rail, which is why the final height for these modules is 128.5 millimeters for all these panels. So for the height, this is kind of the gold standard that you should gun for. So we already know that 128.5 millimeters is the height that we will be going for. Now this is easy because there's one height. There are different standards, blah, 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 but the standard eurorack module is going to be 128.5 millimeters high. So we can just pick this. Now the thing that is going to give us a bit more of a headache is how wide is our module going to be, because here we have the freedom of choice. So we can make this as wide or as narrow as we want. And you probably already know this, like whenever you go module shopping, you will look at the HP. And these kind of describe like how wide a module is. So, and the units here are, again, a bit confusing. So 1 HP translates to 5 millimeters. And then you can see that there's also some weirdness here going on with these kind of levels, because then 2 HP is 9.8 millimeters, 4 HP is 20, 6 is 30, 8 is 40.30. Whatever. Just don't question it. Just stick to this and you will be fine. And for us, what we need to kind of now decide is how wide is it going to be. And kind of the rule of thumb, like if you're starting out, is go a bit wider than you would like, because you need to be able to fit all the components onto the board. And especially if you're starting out, you don't want to cramp everything and make your life really hard. That's why it's kind of advisable to go wider than maybe seems necessary. So in our case, I think for now I will just gun for 6 HP. Probably you could like slim it down in the end, but let's start with that. And so we know that the module width in the end should be 30 millimeters. Now, one thing to note here is that right now we are not talking about the front panel. You know, like what you see here in this picture is going to be the front panel. So you can already see the mounting holes here, you know, top left corner, top right corner, bottom left, bottom right. But we are actually creating the board that is going to be behind the panel. And that board should not be as tall as the actual front panel, again, because of the way it's going to fit into the case later. Because you have these rails, you know, these rails that are going to be behind those mounting holes, and so there's like a certain amount of space that should be reserved for those rails. So what I would just now, this is just like a gut value, what I would gun for is, like if the entire thing is 128.5 millimeters, let's just gun for 100, I would say. So then we leave about 50 millimeters, 1.5 centimeters at the top and at the bottom. I think this should hopefully be fine. Correct me if this is wrong. I will quickly go into the chat. And you are still talking about the power supply connector. Okay, so let me jump back in here. So we will just assume that 100 millimeters is fine. I think to verify this, we can do a dirty trick, and we can. Okay. So let's first apply these values that we just found. So I will say the start X and the start Y is at 0 millimeters. So this is going to be our starting point, which is 0, 0. And then for the height, we said we wanted to do 100 millimeters. And for the width, we said, well, we saw in here that it should be 30. It's advisable to go like a little bit smaller, just to leave a bit of breathing room. So I will go for 29 millimeters here, I think. So 29 and say apply. And now we can see, whoops, oh, this is already kind of scary, because it might actually be a tight fit. I hadn't expected that. Okay, just for the sake of simplicity, to make our lives not too hard, I would say that maybe instead of 6, we're just going to gun for 8 HP, which might be a bit more forgiving. So now the question is, how can I... is it in here? Yeah, set board outline. Yes. And here I will simply go for the next level here, which is 4 HP, which is, let's go for 40 millimeters. I think it's going to be okay. So we're going to set this at 40. I'm going to apply this. Okay, now it's going to be easy peasy going, hopefully. Okay, but let's quickly verify that this will work. So I will take my diode ladder filter, and I will check that PCB layout, and I will check the board outline here, and we can see the height is 109.5. Okay, so we just left less than 1 centimeter top and bottom. Yeah, oh well, I mean, it's not that important in the end. I mean, and you can see that there's a lot of empty space up here. So maybe going with this format here is not the worst of ideas. Okay, so the first thing I will do is I will take all these components and I will move them away. And you can already see, like, this is very important, you can already see these blue lines that are being drawn between our components. And this is aptly named a rat's nest, and it does look like a rat's nest. And what this is this is kind of the software telling us, hey, these components need to be connected together. So all the lines kind of indicate that these are components that need to be connected. But for now, I wouldn't worry too much about this. So the way that I like to kind of approach this is I like to say, well, the most important thing is the user interface, right? So if you build a module, the important thing is actually that it's kind of usable. And that's why I like to always start with placing the interfacing elements. Now, in our case, this is actually very, very simple to do because we only have 3 to be precise. We have the potentiometer, which is the tuning potentiometer, and then we have the two jack sockets, and that's it when it comes to interfacing elements. So let's start by placing those. So traditionally for VCO, you would want to have this tuning knob at the top. So I would like to place it somewhere around here. Now, if you want to be like super OCD about it, you should probably zoom in, and you can see, you know, the whole thing is 40 millimeters. So maybe try to align this thing. Whoops, it doesn't work. Maybe try to align this thing here with the 20 millimeter mark up there. Then you have it nice and centered. And I think this looks okay for now. And then we should worry about the other 2 interfacing elements, which are these 2 jack sockets here. Now let's go back to kind of identify which one is which. Socket 1 is the CV input. So I would like to place this at the bottom and on the left side. And I would like to place the output on the bottom and on the right side. This is also kind of standard to do. I see like most manufacturers are kind of placing their jack sockets at the bottom. And I think it's a good practice, kind of. It works for me. I've already done it this way. And yeah, I like it. That's why I do that. Okay, so we're going to place this here. And now our interface is already done. Maybe drop this a bit down. Then we can use a bigger knob, which will be nice. Boom. Okay, I mean the details are kind of up to you. Like if you want to make this look nice, feel free to make this look nice. Okay, so let's just settle on this for our interface. And I will quickly check the chat if there is anything you would like to add. You are still talking about the net. Yeah, I guess you're fine. So I will just simply go on with the PCB layout here. Okay, so just to reiterate, we have created our interface, which is small but functional. And now the next thing that I would probably do is I would like to place our power connector. Now, what's the best way to do this? Well, it's actually quite simple, and I can show you on my filter PCB. So if we look at this, we can see that this is basically the side that we are looking at right now. So it has a back side, it has a front side. We are looking at the front side. So I have been placing this kind of potentiometer slot in there. So what we will do is we will put our potentiometer, oops, it doesn't work, in there in the end. And then this kind of mounts to our panel. We put on the knob, blah, blah, we have a nice module. Now, we could place the power connector also on the top. Let me check where we would go here. But this is a very stupid idea, because if you put the panel there, then obviously you can't plug anything in there. So a big no-no, which is why you should always put the power connector on the other side. So this way, your power connector sits here. Your panel goes on here, and you can plug in the power on the back side, which is how it should work. Now the question is, how do we get there in our software? Thankfully, it's not very hard. So what you need to do is you need to use this window, which is called Layers and Objects. As you can see, at the moment, we have the top layer selected. And we can see that because there is a pencil in this red field next to the top layer name. So this means that whatever we do, like wherever we drag our components, they are going to be, or we are editing right now on the top layer. Now, but we said that we want to put this connector on the bottom layer. So what we need to do is first, we need to click on the blue thing here so that we now switch to the bottom layer. So now we're editing on the bottom layer. But then you're going to notice that this header now is kind of transparent. So it doesn't look like it's kind of active anymore. So what we need to do here is we need to select that. We need to go into the sidebar here, component attributes. And the top property here we can see is called layer. And there we can see the top layer is selected. If we click on here and we change this to bottom layer, then we can see that now this is kind of highlighted. Also the text has been like mirrored, and this kind of indicates to us that this is going to go on the bottom layer. Okay, perfect. So then what we do is we pick this up and we basically place this somewhere on our PCB. And I think what I would like to do is I would like to turn this. And now, I mean, I kind of saw also people like putting the connectors like in a standard place, something like top left corner, something like that. Like in the designs that I made up until now, I kind of opted to put them wherever they are needed, so wherever they are closest to the places they need to deliver power to. In this case, not quite sure. I think I'm going to put the chips down here. So let's try and put the connector down here. Okay. And now kind of the most important things are basically placed. And then what I like to do is I like to place all the remaining components also on the bottom layer. So on the back side of the PCB, which we are already on. But in order to do that, we need to select all of these components here, and we need to put them all on the bottom layer. Boom. Now they're all green, and now they're all on the bottom layer. Don't ask me why they're not blue, because here it's blue and they're green, but yeah, whatever. That's just how it is. Okay. So what we will start out with, I would say, is we will start out with the Schmidt trigger inverter chip. So I will turn this on the side simply because it aligns better with our layout. I will take this and I will place this. Where will I place this? I think I will place this here. Oh, it's super weird that it has so many connections. It's because of the ground and the power pins. Okay, that does make sense. But the question is, which inverter are we actually using? We kind of find out like this. Are we using the top one? Well, we're going to find out in a second. So let me drag this over here. So intuitively, what I would do is I would place it next to the power connector, if it is connected on this side, and then I would pick up the TL072, this one, the op-amp chip, and I would place this basically close to the output socket. Simply because, I mean, all this op-amp does is it kind of takes the signal from our oscillator and it kind of feeds it into the output. So it makes sense to place it between the op-amp and the output. So I'll place it somewhere here. This still looks a bit messy, but we will see if this makes sense in a second. Okay. And now the next thing that I would probably start with is I would like to kind of place our reverse polarity protection. It's because it kind of belongs to the power supply. I think it makes sense to put this in here. Let's try to find out where it connects to. So it connects to these guys over here. I think the first thing that we should maybe do is we should connect all these ground pins together already. So this is how this works. So you go, again, you go here into this little menu, which is called PCB tools. You select this option, which is called track. And then you basically just draw your lines, right? Like this. Oh, and I'm already seeing something that is not a good idea. This is something that I kind of picked up in some forum somewhere. Whenever you are drawing connections that are meant to like kind of carry power, like from or to the power supply, you should make those routes or tracks wider. So right now, I've selected this track tool, and you can see that here in the sidebar, we have this property, we have this heading called other, and then we have a property called routing width. This will determine how wide the tracks are that you are drawing. Right now we are at 0.254 millimeters, and from what I've heard, for these power connectors, a proper value would be 0.6, which is quite thick. But apparently it's better for the power connection. At least that's what I've heard. Correct me if I'm wrong. But I've done this like this always, and it has worked. So I'm happy with that. So we'll keep doing it like this. Okay, so now I've connected all the ground pins together. I'm just kind of the first thing we need to do. Next thing that we should do is we need to connect our diode here, which is the reverse polarity protection diode. And we need to connect this to our positive supply. So I will place this here. I will select the track tool again. This is still sitting at 600 millimeters routing width, so this is fine. We will connect these two pins together because, you know, these are plus 12 volts or minus, I think it's plus. And we'll connect this to our diode. Now you will notice, maybe if I zoom in, you will notice that it is drawing this track in a kind of weird way. So you can see that there's a weird 45-degree angle. Now you might ask, why aren't we doing a 90-degree angle? And why is this weird tool not allowing me to draw 90-degree angles? It's actually very easy. As far as I know, the problem with 90-degree angles is that the technology of kind of creating the PCB in the end tends to have trouble with 90-degree turns. And maybe there's also something about induction, I'm not quite sure. But in the end, it's a kind of best practice to only use 45-degree turns because for some reason, this is better for production process, and for some other reasons, just keep in mind, always do these 45-degree angles. So whenever you need to do angles, if you can do a straight line, you can do a straight line, it's fine. But if you do these angles, do 45 degrees. So we connect this here, and we can be properly happy with that. Okay, so next I will pick up the other protection diode, which is this one right here. And we will drag this over here. And this one needs to face in the other direction. And we put this in kind of symmetrically to the other one, like that. And then same story here. We select the track tool. We connect these two connectors. And we connect this one to our diode, again in a 45-degree angle. And now our reverse polarity protection is already in there. We should adjust this label because this will be printed, and if we put this off the board, then they will probably have a hard time printing that. So let's put this on here. It's gonna move this one, boom, make it look nice. Okay, so power is kind of settled with that. So then we can see that our chip here, our 4106, also needs a power connection, and it should come from this diode, because remember, the diode is protecting the chip from reverse polarity. So what we do is we kind of just simply move over from our diode to our chip. Boom. So that is that. Now you might ask, why am I not doing the same thing for the ground connection? Like, why am I not pulling this over and connecting, you know, all these inputs here to ground, and then also this pin on the chip, and blah, blah, blah. And the answer is because we are going to use a way more convenient solution for that, which is called a ground plane. A ground plane is basically a layer of copper on the board that connects all the points that need to be connected to ground together. You don't need to route them. That's why we can ignore that for the second. I will explain this more in detail once I will implement this. But for now, just know we can ignore all the ground connections. We don't need to draw them explicitly. Okay, so we've powered this chip, but we also need to power this chip down here, right? So we can see this wants to go here. And that is why I will do this. So let me draw this here, and we have connected this to the negative supply. And we will probably also need to connect this to the positive supply, right? Yes. Okay, boom, we're going here. And now, assuming that we're going to do the ground plane later, we can consider our chips to be properly powered now. Okay. And now you might already be horrified and saying, oh, well, when you're drawing these tracks here, are we going to run into trouble with our remaining components because, you know, there's not much space left? Yes, but we have a trick for that. I will show you in a second. Okay, so the next thing that I would do is I would place the decoupling capacitors. So these are the caps. Let me go back to this view, and we can see that we have the caps C3, C4, C5. We kind of determined that C3 is supposed to be the decoupling cap for the Schmidt trigger inverter. So let's find C3. It's this one here. Okay. What we will do is we will try to place this as close to our pins as possible. Now, here it is kind of complicated because the pins are quite far apart, unfortunately. So I'm just thinking maybe put it on the other side. I'm not sure if that is such a good idea if they are too high, but then again they won't be, like, they are way lower than the potentiometers, so they should fit between the PCB and the panel. Okay, so let's try this. Let's switch this up to the top layer. Let's move over here. Let's pick this thing. Oops, not that one, this one. I will turn this to the right. And now, if I place this correctly, I hope this is not a stupid idea, but I think this might actually work. You know, we put it here straight in the middle. And then what we do is we simply connect. Whoops, now we want to draw this on the bottom layer. We want to simply connect our capacitor with the power and ground pins. Do we actually need to connect it to the... I mean, we're going to use a ground plane, so I don't think we actually need to do that, right? Well, I guess we can take this one, but this one needs to stay in there. Needs to stay in here, definitely. Okay, so now we have decoupled this chip, and now we only have to decouple our op-amp over here. For that, we use the caps C4 and C5. So let's move these over here, and this needs to be as close to this pin as possible. So we can simply put this here. And you shouldn't put this too close because then you will get a warning. It will not be ideal. Put it, you know, reasonably far apart, but then as close as possible, if that makes sense. So put this in here, wire this up. Perfect. And again, the other side needs to connect to ground, yes, but we will use the ground plane for that later on. Okay, C5 then needs to connect to the negative supply pin of our op amp, and we simply wire these up, and boom. And now we have basically everything set up to now, you know, properly do our layout. And now you might already be asking like, oh, how do I know where to place stuff? Like, you know, what if I do something wrong, blah, blah. The thing here is, my best advice is just try it. Just put stuff down, place it somewhere, wire it up, just go on. And at some point, if stuff doesn't work out, you can always change the position, redo stuff. That's how you learn anyway, so don't be afraid to do that. Let me check the chat real quick, if someone said something. So, in EasyEDA, I run the auto tracer and see how far it gets, then manual route the rest. Yeah, I tried that, but the last time I did that, it just didn't really work at all. So I kind of didn't do it again, but maybe it works. But for now, let's just do it manually. I think it's just better for understanding. DevJuck says, after the zombie apocalypse, I'd probably go full dead bug style, copper tape and spade lugs everywhere. That sounds very good. Roland says, shouldn't be as close to the VCC pin as possible. Probably. You're probably right. Maybe I will adjust this. That's why I like dip trace. It routes, auto routes everything. I just hand route to make corrections I find. Lazy guy, this Moritz, there is no dedicated ground plane on single-sided boards. I'm not entirely sure if I get what you're saying, but I get that you say I'm lazy. Okay, let's just finish this layout off. Okay. So the first thing that I want to add now is I want to add the diode that is kind of configuring our Schmidt trigger inverter. But I can't find it. Ah, here it is. So let's pick this one up, and we'll put this in here, and we can check what it connects to. And as we can see, I kind of messed up here. So I kind of expected the chip to be oriented the other way around, but unfortunately it's not. So what I will do here is I will mirror this. I can't mirror it. Oh, this is annoying. This is very annoying. I can turn it probably, right? Like this. I think that's better. But then I need to kind of readjust these connections here. Very sorry if this is boring. Hope you forgive me. Okay, so put this guy in here. Probably need to keep an eye out for the VCC pin. I think it was this one, right? Was it that one? Yes, that's the plus 12 volts pin. So select the routing. And we need to connect this to, oh, there's a right angle in there. That's not good. We need to connect this to the VCC of this one. Oh, and this is now not connected to anything. So we need to connect this one to the positive, so to the diode, which is protecting our chips. God bless him. And then the ground one we don't need to connect, which is quite handy. And then we should move this one as close to the VCC pin as possible. I think that's quite correct. Someone kind of said this. Okay, so now we can move this again to the bottom layer, which is more consistent with all the other stuff. So I will simply move this in here. I will connect these two guys up. Boom. And then we are going to go for the diode here. So select this one. and we need to find out where this needs to go. And we can see that this side needs to connect to this pin and this side to this pin. So I'll simply select this, turn this, move this down here. And as we know, the input is way more important than the output. So we can basically just block the output kind of like that. Yes, and now I will choose the track tool again. And now since we are not doing power connections right now, so all the other traces that we have drawn are power connections. So now what we should do is we should tame this a bit. So I tend to go down from 0.6 to just 0.3 millimeters. And then we can simply wire this stuff up. We can simply wire this stuff up. And that is our diode done. The next element that I would do is I would do the capacitor here, C1. So let's go for C1, which is this one here. Place this here. We should probably turn this. Let's find out. Okay, so this point here needs to connect to the input. So that's why I will turn it this way. Drag this down here. And now we need to be a bit careful because we don't want this to cross kind of this this connection here. So I think what I want to do is I think I want to move this here just because of space reasons. So I'll move this here, and then we can see that we have some space to navigate behind. I don't know if that fits. Let's try this. So what I'm thinking is go from here, basically through here, and go to this point. So let's check if that is possible. It's actually not necessary. We can just come from here. Sorry. That's actually what I like about this. It's a bit like solving a puzzle. Boom. Okay, so now we have our diode and the input connected to our capacitor. And again, the other side is connected to ground, but we don't need to worry about this because we have the ground plane, or we're going to have the ground plane in the end. I think I want to move this guy up a bit, just simply because it gives us a bit more space to operate. And this doesn't need to be pretty. This just needs to be functional. Okay, so then the next element that I would like to put in is probably the transistor. So this is transistor Q1. Let's find this guy. And it's down here. Just waiting to be placed somewhere. And I think I want to... Well, now there's kind of a dilemma because we get our CV signal. On the one hand, we get it from up here, from our potentiometer. And on the other hand, we also get it from down here, from our socket. So either way, we can't really win because we can't really put it in the middle because there's not enough. Come on. There's not enough space here in the middle. So I think I will put this up here where there's a bit more space. Okay, so let's identify which pin is which. So the pin on the right, you can see this pin here, this connector here needs to connect to our capacitor. The other one goes to ground, and then the middle pin goes to the other transistor, and so on. So what I will do is I will turn it this way, just so that the bottom pin is closer to the capacitor. And maybe we will place it somewhere here. Doesn't really matter. Boom. Okay, and then one thing that we need to keep in mind is that these transistors should be as close to each other as possible, because in the design kind of depends on the fact that they are at the same temperature. So what I would probably do is get them really close together so that you can use thermal tape to glue them together, if you're so inclined. The question is like, how close can we get them together? But I guess something like that should probably work out. Okay, now we need to wire them up. So we can see this this connector wants to go here, so we can just do him the favor, make him go here, and then we can see that oh, this actually also wants to go here. That's weird. Ah, yeah, of course. This wants to go to -12. And of course, the potentiometer is also connected to -12. So it makes sense that this would go here, right? Okay. But then again, this also needs to go to -12. And now we run into a bit of trouble already, because you can see we can't really go through here. Because we can't make routes cross, because they would connect as long as they are on the same side. So this is kind of a problem. And also we can't navigate through here because it's just blocked. We can't get there through here. We could try to go around here. And this might actually work. It's not the prettiest thing in the world, but if the software allows us to do it, usually it will work in the end. Then we also need to go around here. And we don't want to do a 90-degree turn, so we go here, and then we go up there, and boom. And it worked, kinda. Okay, so we have these guys wired up. And then what else do we need to do? So this connects to some other element that we haven't placed yet. This one needs to go to our capacitor, which is something that we can just quickly do here. Again, with the 90-degree turns. No. That is not correct. So go over here, and boom, that looks better. Okay, so this connection is also drawn, which is nice. And now, of course, this one needs to go to ground, so we can completely ignore this, again, because of the ground plane we will put in at the end. And so now we need to kind of complete the circuit here. So first, on the emitter, on our PNP transistor, which is the one that we have placed here on the left side, and this one here is the emitter. This needs to connect to the 1 mega ohm resistor that we have flying around here somewhere, which is called R1. So let's find R1. This is 4 through 8, and here is R1. Perfect. So we will pick up R1. I'm kind of starting to fear that this might actually be like a tight fit, which is a bit annoying because 8 HP is already quite large. But yeah, I guess if I wasn't doing this on camera, it would potentially be a bit easier to do something nice. Okay, let's turn this on the side, because I think we can make it fit like this. Hopefully, yeah, that should work. Okay, and we'll draw a connection here, and we'll draw a connection here. And I'm guessing you can already see the benefit, like I explained in all the way in the beginning. You can probably see the benefit of creating this schematic first, because it simply allows you to kind of go by autopilot, because you know the software tells you which components need to be connected, which is super helpful. Okay, so this one is wired up, and then the next thing that I would want to do is probably get these things. So R2 and the trimmer. Let's start out with R2, which is down here, and we will drag this guy up here. I don't really think that anything speaks against just putting it somewhere here. I think this should probably be okay. Now let's get the trim pot first to kind of evaluate this, which sits here, which is quite huge. Okay, but whatever, we don't care. We should turn this around, because you can see the bottom connector needs to connect to our Oh no, it actually doesn't need to be, because the other two connect to ground and the bottom one connects to our resistor. So we can basically just put them here, and then our tuning trimmer is going to be here in the top left corner. Okay, and these are now very easy to wire up. So we connect the trim pot and the resistor. We connect these two together, and they need to connect to ground. So we can just leave them dangling, and they will be taken care of by the ground plane in the end. Okay. Next thing. So here we run into trouble because again we see we can't go through here, right? Because this is blocking. But now actually instead of going over here and then circling back there, I think what would be nicer is just to go to the top layer, because we have two layers. That's a good thing. So we can have traces on the back and we can have traces on the top of the PCB. So if I select the top layer here, then we can actually cross this other trace, simply because we are on the other side, and these now don't make electrical connection. Now, one thing to keep in mind here is, at least that's what I've read, you should not have them go parallel to each other, very close to one another. So this is why I made sure that these cross at a 90-degree angle, like they're not parallel. I've heard that if they go parallel, there might be some weird like capacitance stuff or noise or whatever going on. So just to be sure, make them cross at a 90-degree angle. That's what I've heard, what you should do in this situation. Okay, so we've wired that one up. And now we have, whoops, oh no. And now we have basically already this whole part here done. So now what I would want to do is I want to finish up the coarse tuning potentiometer, which is this part. And we already have, of course, a potentiometer here. And now we just need to place R2 and THM1, which is the thermistor. So R3 and THM1, let's pick those up. This one is R3. So we will drag this guy up here. Now I need to think. Okay, so after this, they need to go where? After this, they need to go to the base of the PNP transistor. So maybe it makes sense to start with the THM1, which is this one. Whoops. Keep moving the wrong, no. Keep moving the wrong things here. Okay, so let's pick this guy up. And yeah, the idea here is we want these thermistors to be also to be as close to the transistors as possible. So this might seem a bit chaotic, but I will again try to place it quite close to the transistors here. I can already wire this up because this is kind of an important connection. And we can't make the connection. Because it can't kind of leave here. Okay, so what I will do is instead of coming from this point, I will switch over to the top layer and I will simply come from the connection here, because it's all the same. I mean, if this kind of track connects to the base of the transistor here, then you can just connect this to this point, and then this point and the transistor's base are still connected. Like it doesn't matter like where you actually move them. So this is going to be fine. Okay. And then what we need to do is, wow, this is kind of a tight fit. Don't really feel this is very representative. So if you do this yourself, I strongly encourage you to build a nicer looking layout than what I'm doing here right now. Okay, so let's put this here. Let's simply draw this up here. And again, you can see I am making them cross here at a 90-degree angle. I avoid having the blue and the red lines be in parallel while they are kind of overlaying each other. Okay, and then the next trace here is going to be towards the middle leg of this potentiometer. And now we have the coarse tuning set up. And oof, this is really kind of messy. I apologize. Okay, so the next thing that I would do is I would set up the other thermistor, simply because also this one needs to be close to the transistors. So I will simply place them, or place it here on the other side. And then, I mean, because the thermistors have long legs, we have some kind of wiggle room here, and we can get them very close to the transistors, and we can kind of glue them together as well, and so they're all at the same temperature, and our circuit should work just fine. Okay, so now that I've placed it, I should be able to draw our connection here. But again, we can see there's a blue line in the way between these points. So I'll switch over to the red line, to the top layer, and now I can again just simply cross the blue line. And I think it's most elegant if we do it this way. Again, crossing at a 90-degree angle. This should be a good thing, hopefully. Okay, so this is the THM2 now done. What we want to do now is we want to use R4 to connect to our CV input. So let's swap in here. Let's find R4, and we can see that it is on top here. I will move this here, and this is now basically the connecting piece between the thermistor and the socket. So that's why I'm going to move this. I'm going to move this, yeah, I guess next somewhere here. Like we shouldn't make this collide with the power rail, but I guess here probably for now is as good a place as any. I will pick the trace tool again. I will route this to the thermistor, again 90-degree angle, and I will route this down. Probably it's going to be hard to get a 90-degree angle here. Let's try nonetheless. That is not the prettiest thing I've done. Well, I mean, the main thing is it should work, right? I guess this will probably work. Still, I'm unhappy with this. Let's try something. Yeah, I think this looks better to me. Okay, so this is wired up too. So now what we have is we have all of this and the oscillator core, and also the power supply is done. So all we need to do now is we need to buffer, we need to AC couple, and we need to amplify the signal and then send it to the output, and then we are done. Okay. So then let's start with the first buffer. So this is going to be easy. We need to come from our oscillator core. We need to connect to our buffer. Okay, so in our oscillator core, the output is basically here. So we can see that we need to go from the diode here to the op-amp down here. Again, since we're on the top layer, we can just cross the blue lines, and we can just simply go straight towards that point on the op-amp, which is great. And then from here, we need to connect. The input and the output. I'm very unfamiliar with the TL072, so I'm actually unsure which point here is which. But yeah, so this seems to be the inverting input and the output, so we connect them. Okay, and then the next thing we need to do is we need to pick up capacitor C2, which should be floating around here somewhere. I think this is it. Yes. So this one connects basically this side of the op-amp with the other side of the op-amp. So we need to put it in a position where it can kind of mediate between the two. Now, one thing I would like to note here is while it is possible to put stuff behind these Thonky connectors, and also, oh no, actually here it's not possible because there's a big hole in the center, but it would be possible to place stuff behind the potentiometer. I would really discourage it, because the potentiometers have like all these metal bits, and if they, like, there are some spots here on the potentiometer where they will touch components that you place behind them, and you can have weird effects, you can have shorts, so I would strongly discourage you from placing stuff behind the potentiometers. I mean, again, down here it's not so big, that big of a deal, because there's a gaping hole in the middle of these jack sockets anyway, so you can't really place anything there anyway. So let's put this here, and we will wire that up again, 90-degree angle, which is the way to go here. I mean, it's going to be okay. Boom. And then on this side, we need to connect to this connector. And we can see that we also have R5, which is going to ground after the capacitor. So let's pick that up real quick. It is here. And now we kind of have the choice where we want to put this. And I think it's best to just put this down here. I will turn this, and we can see that this footprint is really, I would say it's too large. It's unnecessarily large. It would fit here. Yeah, I mean, I guess I'm going to put this here. It's going to be okay, hopefully. So maybe align this a bit better. Boom. Connect these points. And now what we have is we have this buffer, we have the AC coupling. Now all that's left to do is the amplifier, and then we can connect to the output, and then we're done. Okay, so for the amplifier, we need to connect the AC coupling to the non-inverting input, which is the first thing that I will do. No, I've already done this here. Perfect. Cool, so then we need to configure this as an amplifier. So we need R6 and R7 for that. And again, these things are ridiculously big. So I guess next time I wouldn't really pick smaller ones. I think they're even too big for the quarter watt resistors. Yeah, anyway. Okay, so the top one needs to connect to our op amp here. So I will simply turn this to the right. And again, the bottom one goes to ground, so we can ignore it and let the ground plane take care of this in the end. Yeah, I think I will place this here. Zoom in, connect this thing up, and boom. And then we need to take care of, of R7, which will go, this will be a bit more problematic to make it fit here. Well, between these 2 points, it needs to connect. Okay, and this is really where this starts to feel like a puzzle. Well, maybe we can actually put this in here somewhere. This is very ugly. I can put this in here. Probably should turn this twice. Yeah, if we do it this way, it is unorthodox to not call it ugly, but I guess it will probably work out. There's a red one there. Okay, maybe this is a good. I'm not claiming this is a great layout, but this might be as good a spot as any to teach you about vias. So I mean, what you can see here is we are on the top layer, and we are able to jump over this blue one, but we're not able to cross this red wire because they're on the same layer. Now, there's one secret tool that you should probably use as as not often as possible, but I'm going to show it to you. So what we can do is, when we see that this is the end of the line, we can't get any further from here, we just right click, and then we simply have a connection that goes nowhere. Now what we can do is, in this tool, we can select something called a via. I'm not sure if I pronounce this correctly, but this is it. So what that does is, if you take this and you place it at the very end of your trace and you click, then this allows you to continue the connection on the other side of the board. So right now we are drawing on a red line, which means that we are on the top layer. And what we can now do is we can switch to the bottom layer and we can continue drawing here, and boom, and then we can jump over this red trace. And what this allowed us to do is we were allowed to go from this connector to this connector while jumping, traces on two different sides, which again, it looks very messy. I'm not proud of this. But yeah, that's how it is. Okay, so let's finish up. The last thing we need to do is we need to take this resistor and we need to place it between the output of our op amp and the output socket down here. So I think what I will do is I'll turn it this way. I'll simply place this here. And then we need to kind of find a way to navigate this madness here, but I guess it should be actually doable. So if we go to the bottom layer, which we are already on, and we come from the op amp's output here, then it is actually no problem to get there. And it's also no problem to get to our output socket here. And again, this label is now off the board, so we should kind of move this in here. And of course, if you build this yourself, be sure to make the labeling kind of neat and tidy. Like, this is a bit of a mess. But yeah, now we actually managed to place everything on our board and it won't stop scrolling. Okay, so boom. Again, not claiming this is a great layout, but I hope this kind of showed you like the basics of how you can wire stuff, like what you need to kind of look for. Okay, but now the final thing that we need to do is something that I have been talking about for the last hour, I feel, or even longer, is we need to put in the ground plane, because as you can see, there are still a bunch of connections that need to be made. So if I highlight this, you can see, like there's a bunch of stuff that's not connected. And the way that we will get rid of this is by zooming out, by making sure that we can see the entire board. And then what we do is we select this tool, which is called copper area. We select that. Then it kind of prompts us to specify what this should be connected to, or kind of what this should be the medium for. And in our case, it should be ground. It was already selected, but yeah, select ground again. Put that in there. I prefer to do this on the top layer. You can do it also on the bottom layer. It doesn't really matter. And then what you do is you simply draw a square around your board. You don't have to be precise about this. Just make it roughly around the board. And then once you're on the third point, you can right click, and then you can see what it does is it, like, all the red stuff now is the ground layer. So this is all connected to ground, and you can see it automatically kind of insulates everything that shouldn't be connected to it, like from that ground plane. So here you can see you have this trace, but there's this empty area between this and then the ground plane, to just make sure that this doesn't connect to ground. But then on the flip side, all the points that should be connected to ground, like this one, for example, they are connected to that ground plane. Now, one thing that you should kind of adjust here is you can see that there are like these 4 areas that are kind of gaps in that ground plane. And the reason those are there are because if they weren't there at all, so if this point would just be completely connected to the ground plane, the trouble is that this entire surface here is copper, and this entire area. And when you solder to one of these points that are connected to ground, you have like this ground plane is able to conduct like a bunch of heat. And if you want to solder to these points, you will have to bump up the heat on your iron like crazy, and you will have to kind of hold the iron to these spots longer, and potentially this will cause you to damage some of your parts, and you don't want to do this. And that's why these things aren't here. So in the software they call them spokes, I think. So if I click here on this, I hope you can see this, like here, this dotted line, which kind of indicates our ground plane, or it stands for our ground plane. If I click on this and I go to the right side, you can see it says copper area properties. And here you can see 2 things. So first, pad connection has already this option selected, spoke, which is what that's called here. And then it has here a property called spoke width. So right now this is set to 0. Now strangely in EasyEDA, 0 means that it's set to the default value, which you can see here, which why you can see these gaps. But for my tastes, or when I had my first run of PCBs, this was kind of, it was still too much connection to the ground plane. It was still hard to solder to these points, which is why now I kind of opted to make them kind of bigger. So let's try to set it like this. Let's say rebuild the copper area, and nothing happened. That is very weird. Let me bump this up and then see what happens. Okay, so for some reason this doesn't have any effect. That's very weird. Let's check the other ones. They look the same. I need to make them smaller. Do I? Yes, okay. If I do 0.01 millimeters, that's extremely small. Maybe that's too small. Maybe do 0.02 to, I don't know, you have to help me out here. Like someone in the chat probably knows what the correct value is for this. I'm going to go with something like, no. It seems like now it's all the same. No, it doesn't change anymore. No, it changed. No, it changed. 0.5? Yeah, I guess this is probably an okay value for that. Maybe you can go even smaller, I'm not quite sure. But yeah, now you can see that all these connections here, the gaps are much bigger. And this should make it much easier to kind of solder to these points, basically. Okay, so let me save this. And let me center this on the screen. And now what we can do to kind of enjoy the work we've done is we can click on either of these. You can't see my cursor, but up here in the kind of navigation, there's 2 options. The one is labeled 2D, the other one is labeled 3D. And if you click on either of those, then you will get kind of a preview of how your board is going to look like in the end. And I'm just seeing that are we missing a connection here? Are we? No, it's just drawing that there. Okay, cool. Okay, so let's go into the 3D view. Okay, and the cool thing here is you can, of course, you can rotate it. You can look at how it is going to look like once you order this, and then for some parts, For the TL072, for example, it already like renders it in a 3D way here, which is quite nice. And yeah, what I like to do is I like to change the board color. Like my preference is white, but of course you can try this out in different colors and see how it's going to look. So here we have blue, we already had that, red, or black. I think black is very popular with the kids. And yeah, but white is what I like. So this is how I would kind of get this made in the end. And again, this layout is not ideal. I will probably clean this up a bit, but it should actually be functional. And just for completeness sake, I will also show you the 2D view. So this is how that would look like. That's basically an inferior version of the 3D view. But yeah, that is how you create a PCB. To be honest, I think I will not do the panel today, simply because it's already pretty late here, and I think I don't want to rush that. So I think I'm going to do like an additional stream on how to create panels here in this software, which is what I did for my filter module. But for now, I will jump back into the chat and I will see if you have any questions. So give me a second. Oof. Okay, let me scroll a bit and let me check this. Change back to blue. Oh, this was earlier about the bias. Click the rebuild. Yeah, I did that. We already passed that, so I need to scroll down further. I should do that. Those ground planes are really hard to solder if they are connected that much. Thermal mass gotta heat it up quite a bit. Yeah, it's super annoying. Like for my filter module, that's actually what I had to do. Like I had to really bump up the heat. I was really scared for my components. So yeah, I think it's really smart to make them wider, like these spokes. Lucas is asking, should there be a blue ground plane? It depends on which side you are using. You can use either side. You don't have to use both. So you can have the ground plane either on the red side or on the blue side. Doesn't matter which one you pick. Just, do it as you like. Okay, Marcus says, so you know the schematic inside and out and you didn't breadboard your modification, but usually you would recommend breadboarding the circuit after adapting it or something. Yeah, this completely depends on how well versed you are with the circuit you are building. If it's something you build yourself, probably you can make these adjustments just freestyle. I mean, we didn't add anything, we just took away stuff, so it was actually, I think, quite easy and quite risk-free to do that. So yeah, I think in this case, not breadboarding it is fine, but usually you should probably breadboard it, yeah. Black looks the coolest. Yeah, I tend to disagree. I think when it's made, the white stuff looks just fancy. Maybe it's just my taste. Eloth asks, what is wrong with the layout? Well, it's just, because I am on camera and I kind of didn't take the time to line stuff up and to kind of group stuff a bit better. I feel like it is a bit all over the place. I'm not saying it's not usable. It's definitely usable. I would just, if I had more time and less stress, I would kind of opt to make it a bit more nicer looking, I guess. That's the only complaint I have. George says, white or purple? I haven't tried purple yet, actually. Let me just switch quickly over to purple here. Let me go into the 3D view and let's select purple. Oh, yeah. That's actually not bad. And then if you do the front plate in the same coloring, it could actually look quite nice. True. Okay, we switch back to the chat. Since the ground plane is basically a large amount of copper, it will take a while to heat it up to the point where the solder will flow on the joint. Yes, that's the explanation. True. Wonky Robot says, pink is the only right PCB color. Okay. The Art of Fencing says, are there any other things why you shouldn't do a ground plane? I think there are certain considerations when you are doing, I think, digital circuits. If I remember correctly, there are some reasons when you should rather use a star ground, I think it's called, as where you basically have multiple connections that are going to the same point. But I think for our use case, so for synthesizers, I think a ground plane is perfectly fine. So and it's easy to do. So I think it's a good choice there. ID3M says, can you make this layout shareable on EasyEDA? Yes, I can. I guess I can do that. I will do that later on when I kind of revamp all this stuff. DevJog says, no worries, panel design is a whole new can of worms. That's true, and it's like a different kind of requirement. So yeah, I think it's good to kind of separate this out. Bye, SynthUX. Talk to you soon. Hope this was helpful. Marcus, bye. Have a good night. DevJog says, purple is the Olimax de facto color, right? I don't know what Olimax is. Drowning Brightness says, what other things would you look over before sending off to printing? I would kind of make sure, like maybe I would adjust like this kind of cluster here, the transistors and the thermistors, to make it a bit more symmetrical and to make it easier in the end to link them together, because this is kind of displaced. So I think I would kind of redo that maybe. And then for checking, I mean, the most important part is that you recheck the actual schematic so that everything is correctly connected here, that you really make sure that this is how you had it on the breadboard, how it was working. So double check this. And once you've double checked this, then from a circuit kind of perspective, this is going to be functional, definitely. But one thing that I would probably look at is there enough space between components? Is there enough space towards the edges? So there might be a situation where if this capacitor here is too wide, it might kind of, it won't in this case, but it could like kind of collide with the resistor or with the chip. This is something I would look out for. And then, yeah, also, I mean, I didn't do this here at all, but like I said, if you have to place stuff behind the potentiometer, make sure that it doesn't connect with any of the metal parts on the potentiometer. And then, like, this is kind of a shitty advice, but since printing these is so damn cheap, and if you're a beginner, just go for it, send them out, maybe make multiple different circuits, or maybe not, maybe do one circuit, send it out, get them printed, get 5 of them printed, they're super cheap, get them delivered, try to assemble one, and then you're going to see, okay, this doesn't work, that doesn't work, whatever. It's really learning by doing, and I can kind of tell you that you are not going to make mistakes twice there because of the waiting time alone. So yeah, just I would say just go for it, send it off, and then see. Okay, what else is there? Thanks for watching, guys. Olimax is a fast PCB prototyping manufacturer. Okay, good to know. They were basically the budget PCB kings before JLC took over the world. Okay, good to know. Okay, guys. So if there is nothing else. One thing someone asked about, I don't know if that person is still here. What I would just like to talk about really quickly is the progress for my, I kind of announced that I wanted to sell these PCBs and also to sell these filters as kits. And the question in the beginning was basically, hey, what's the progress on this? What's the difficulty? Why is it taking so long? And the thing is that on the engineering side, I have made some revisions to the circuit, and I am quite happy with how the circuit works and sounds and everything. So on that side, I'm actually ready to do this. The problem is just that it's super annoying to get like the legal stuff sorted out. So I don't want to bore you too much with this, but I'm doing this channel as a freelancer, which is kind of easy to handle, like tax-wise and everything, because you don't have to do so much bookkeeping and everything. But as soon as I start to sell stuff physically, things change. I have to do different kind of bookkeeping. I have to get a permit to kind of sell stuff. Then I also need to kind of make sure that there's like certain regulations here in the EU that you need to adhere to if you sell electronics in specifically. And frankly, I just don't have the time currently to deal with all this kind of stuff. And so what I rather do is I would rather focus my efforts on making videos, coming up with new circuits, making new content, just simply because it kind of feels more interesting for me at the moment. Once I have more time, once my regular job also allows it, I will dive into this again. But I'm just saying, like, don't count on having me sell these in the very near future, which is kind of sad. It's kind of shitty, but yeah, that's just how it looks right now. Okay, anything else? If you choose SMD, can you order them assembled? Yes. I think JLC provides that service. And for a circuit like this, I think this should be fine. If you do, for example, my filter here, my diode ladder filter, the problem is that the diodes should be matched. And if you get them pre-assembled, I don't think you can ask them to match the diodes for you. So there you would have to live with unmatched diodes and therefore a bit of CV bleed through. So it depends on the case. I think generally you can do this, yes. Okay, Will says, do you run a design rule check? Yes, actually EasyEDA kind of forces you to do that. I think once you try to export as a Gerber file. And you can also trigger this manually here. And as you can see, I've run this and it says 0 errors. Also, the nets check here has completed, so everything is fine here. So it looks like this design should probably work. Okay, George, amazing stream, by the way. Thank you. I'm very glad to hear. Like, I'm always like with these streams, I'm a bit self-conscious because I feel like, when I do my videos, I get the time to write a script, to be like super focused, blah, blah. These streams always take a long time and they always take longer than I expect. And I'm always a bit unsure if I bore you guys, but if you say that you enjoyed it, then I'm very happy about that. Okay, Lucas says, could a website like Musikding in Bavaria sell your kids? I mean, yeah, I think it would be a possibility to kind of partner up with people like, Schneidersladen or Musikding or Thonk. I think they could all potentially sell these things, but still I would kind of need to sort this out legally. And then in the end, to be completely honest, I would like to have my own web shop just because maybe I'm a bit vain. I think that would be nice. But yeah, maybe that would be a good compromise to have them to get my kits sold by someone else. Okay, DevJock says the same thing. Outsource the bookkeeping and distribution. That saves a lot of time. That is true. I'll consider that. Matthew says, I've done the pre-assembled servers from JLC PCB and it's good, but can get very expensive if you don't pick your components very carefully. I've heard about this as well. Like someone posted on a forum and kind of broke down like what the costs were. And I kind of thought like, of course, this is still cheaper than buying a module, like buying a professional module. But I don't know. For me, soldering also is kind of fun. So I like to do it. So I don't really see a point in buying pre-assembled. Korn says, I've learned so much. It would have taken me all day to figure out myself. Very glad to hear. I hope you do something with this and build a PCB. And I don't know if you're on my Patreon or on Discord. If you are, always feel free to send me your stuff. Happy to look it over and give you an opinion. Raketensasso says, I didn't not to rush you. I was interested about the process. Thanks about the update in this vid. Yes, I to clarify, I didn't feel rushed. I don't feel like I have to push something out. It's just that I want to do it myself, and I feel like I'm just frustrated, because like I said, the engineering stuff is done, and I feel like if I was just done with this and I could push it out, I feel like there would be like a few people who would be interested, and so it's just annoying to me that I can't do it earlier. But that's just how it is. Okay, and I think I just lost the stream. I hope not. Anyways, if I did, very sorry that there's a very abrupt end for this. Okay, one more question. Wonky Robot is asking, is there space for the chip socket? Yes, I hope we're back. I hope you hear me. So I'm just answering the question of Wonky Robot. He asked, is there space for the IC socket? And yes, when I did my first PCB design, I was also very worried about this. And it turns out that these footprints, they accommodate the chip socket very well. So even in a situation like this where the capacitor is quite close, I'm very sure that this will still fit. I mean, worst case, you can bend the diode and the cap a bit to the side, but I don't think it's necessary. But maybe if you create this yourself, you maybe want to move this a bit further away. Of course, it's always better to be safe than sorry. Okay. George says, yeah, I heard Germany has high bureaucracy. Yeah, definitely, especially when it comes to business stuff. So that's just how that is. Okay, so guys, if there's nothing else, I would like to call it a day for now. I will then plan a future stream on panel design. We are going to take this circuit and we are going to make a nice front plate for this in a future stream, which I think is going to be shorter because when we focus on panel design, it's going to be quicker, I hope. Okay, so there's no other questions. So I will wish you a very nice evening or day if you live in the US, and I will talk to you guys soon. The VCA video, someone has been asking, is coming along. Won't be able to do it next week, maybe the week after, or worst case, the week after that. Had a lot of stress with side projects and work and all of that, but I will be getting back. And in the VCA video, you will get kind of a guide on how to use transistors, which will be the foundation for a transistor ladder filter that we will be building after that. So I hope you're excited for this. And with this, I wish you a good day, good night, and I will see you soon. Bye-bye, guys.